Okay. So, Christopher, thank you. So, we have a lot of interesting talk. Christopher is almost finishing his PhD. Maybe before the end of the year, he'll be graduating PhD and he plan to go to postdoc. So, he's working on that. So, while doing that, I am, working on extending my the time physics, the tensor and everything to higher level to do you know the actual experiments to see whether we can do spin spectroscopy, which I showed even in the conference, Budapest conference. And this is, by the way, we are happy that the StreamYard Christopher was able to put in. Thanks to Christopher, now we are back to you know uh, business, resuming our conference thing after our Budapest conference, which was in my opinion, it was a huge success considering situations. Overall, everything worked out very smoothly, very nicely, and we have good view on our thing, close to 400 without any publishing, and that's a good thing. And continuously, people are watching. So we are reaching about 400 without any marketing, without anything, just a bare thing. So if you do marketing, we can do probably 10 times that. But in any case, and other things are, coming along. So this StreamYard will help. And one other thing is that maybe I should show the other one. Earlier, one of the papers I had was, yeah, anyway, spin spectroscopy that also I presented in ICFAS, the conference, the fundamental thing in Turkey that we do every year. So I had that presentation that is in ResearchGate, uh, and that showed a spin spectroscopy where you can see gravitons. So let me see whether I can pull up that stuff. Maybe I should pull up that. Maybe I start with that. Yeah, briefly I'll go through that. I think that's a good idea too. Okay, so let me see whether I can. What? Oh, okay, the other one. Yeah, they have improved the to some degree. I mean, it's about the same, but I think there's some improvement in the way things are working with the StreamYard. So that's a plus point, I would say. Let me see. Not that one. So, mm, let's see. Trying to get the. Okay, I think this is the one. Okay, so let me see. Okay, so this is the one. Um, I'll just leave it directly so I can see it also. Okay, so this is the one, and just move forward to the next slide. So let me move to. Okay. So this is the one that even the conference we went. This is kind of a summation of the results, recent results, converting the theory, the time theory to the tensor theory to experimental design. And I came up with a new way to do the spin spectroscopy. What you call the I just combined the classical thing we all know very well from Rutherford and all ERM ratio. It's a well-known thing, and then combined with the quantum thing. So it's like a hybrid between classical and quantum theory. And the spin number, the spin is the most important thing. As we know, the quantum computing, everything, the spin is the important thing. So we know the fermions have half spin, and the bosons have full spin, and the gravitons supposedly have spin too. And I got a very good discussion from one Professor Borisino when I presented in the Turkey ICFAS conference virtually, that he asked about these questions related to that and some advanced things I have developed. Uh, so let me start with this one. So you have fermions here, okay? All kinds of fermions that I plotted here: electron, tau, and muon, and all that. And then you have bosons, particularly the photons, and also Higgs boson, things like that. But then, what is hiding here, if you extend this theory, is that the spin 2, if it is there, this I don't know, is a very bare thing. There's a graviton here. And when I plotted this, I found that, oh, should I change that? No, actually, this could be really what's happening. So if we do the LHC or some other experiments, and I also in the new OJPS, which is probably will be published in a month or two, I have said how to use this to do experiments with LHC, but also laptop, tabletop type experiments called nitrogen vacancy centers, things like that. So I think that paper considers that how to use this and then come up with the thing. So just uses a jiggling method that you have Thomas precision, Bohr magneton, and the quantum relativistic effects, uh, things like that, Compton electromagnetic effect, things like that. So if we jiggle that, we can see actually, you know, how the fermions are. So we can figure out where they are. And the same method you extend, at least theoretically now, to graviton. You can see whether gravitons really are meaningful, whether they really exist. Even, if you can do this spectroscopy, you can get the result from many different experiments that have plotted. It could be any particle accelerator, things like that. But this result then we extend to the thing and see whether the graviton actually is a reasonable particle and how much energy you need. Probably very, very high energy is not possible with even LHC. But theoretically, can we extrapolate this result to see whether graviton is a feasible thing? And if we can, then it points to a very step forward in understanding the quantum gravity. That the quantum gravity is a reasonable uh, way to unify from and then advance from standard model, which is the accepted norm now. And when I went to CERN, I couldn't go inside, but I talked to a couple of people, and it was a holiday for them. But I still saw very interesting the spiral, I think, which shows everything, including, and of course, they were advertising about Higgs thing and the Higgs photo and the boson, everything was the big thing there. And that's a main attraction. I couldn't go to the visitor center, which may have more things because it was closed that day. Monday, it was a holiday for them. But it's very interesting. I talked to one Japanese student who she was working on the Atlas project, the new project, and I had like a couple of minutes, and then few Japanese guys who are going to stay there, and they're doing very high level group theory and the next level physics and theoretical physics. So they're all onto it. So I had a brief talk with them about our graviton thing and micro black hole, things like that. So that's advanced. So I feel confident that I started from absolute theory, and I mentioned in this paper that indeed, I started from. So I'll just briefly go through these few slides. I think it will help. Uh, so I started from here. Oops, I have this one problem. I have to solve this problem. Okay. I get some glitches in my computer because
Oh,
of the some advertisements comes on,
okay.
but I don't know. I cannot totally prevent it, so I just had to let it go. 1 minute, 1 second. Uh, Let me get out of that.
Hmm. I don't think we
Okay.
can see it,
Mm.
but because you're
Yeah.
sharing
So
a specific thing, are you?
yeah, yeah. So I think you can see this now. So
Hmm.
the first thing is
You might want to make your slides bigger, though. I don't know.
oh, okay. Okay, I'll make it full this thing. Uh, I can
So, how
go,
are you going to
I
extrapolate
can run it,
the spin
essentially I
mass
can
thing
start the
to the graviton? I mean,
slideshow.
in general, we know what the graviton is spin to, and it's massless. So, if you
Yeah,
don't need to extrapolate, do you? Because you kind of know what the answer is, or is that what's your point there? I didn't really understand it.
okay. So, okay, let me go back and get my, I think it jumps, but it's okay. This is the one I presented in ICFAS in the conference.
Okay, great.
Uh,
Yeah,
so
that
I-
was good.
yeah, so I can briefly explain that here. I think it was a very successful conference. Now everything is converted to mostly 15 minutes talk, so everybody has to
Well,
finish
just
it, and that's
just that issue, Rajan. What were you saying? It was extrapolate to
ah
the graviton. How
okay,
how would you do that?
okay.
Well, I
So
mean,
these are
what's
the
the point
things.
in extrapolating? Because you know the answer, don't you?
Yeah.
So
So let me go to that slide. So this is the vacuum induced. Okay. So the idea is that if the graviton exists, it has to be a spin too. I know, right? You agree with that?
yeah,
Uh,
yeah. That's what we're
yeah.
saying. Yeah, that's right.
Yeah. So if we can get this ERM, which is perturbed, the perturbation helps to figure out because the quantum relativistic effects
Wait,
will
the perturbation
change
of what? Sorry, of the.
the ERM, the charge to mass ratio. Because classically we know
Oh yeah.
ERM is, ERM is a well-known constant.
Okay.
It's not as this thing as fine structure constant, but it
Right.
is but it is a fundamental constant.
Oh, that's
Uh,
interesting. I
and
didn't know that. So is that for? Well, I suppose. Well, all the particles will have a conserved constant charge, is it? But their mass
yes,
is not conserved.
yeah, but EORM is a constant for each particle. So you can use
Or
EORM to
how is it a
character.
constant if the masses of the particles can change under different relativistic effects?
Yeah, so this is the change that can happen that I'm showing here. So
Well, no, but
it shows,
that question is kind of important. Is that I mean, I suppose you could say that mass is conserved somehow in relativity, but
uh-huh.
it's happening at a higher level, isn't it? It's like
Yeah,
you're
yeah, yeah, because
conserved
of the
under
ER,
time and space
yeah,
and all of this other stuff. So, but I mean,
uh-huh,
so you could say like, but it's not really a conserved quantity, is it? The mass get
uh-huh.
can get higher and lower. I mean, I think it's a debatable topic. I don't know if I consider charge mass to be a constant, but maybe you're right.
Uh,
I mean,
for an electron, we know specifically,
in a very technical, high level, or way, you're
uh-huh,
probably correct. But I mean, just on a kind of a basic, more what do you call it, like novice approach, which is what I'm looking at it from. Do you know what I
uh-huh,
mean? So I don't really
uh-huh.
understand how it's a constant, but you're confident it is. Is that right?
Yeah, classically. So we have to,
Oh,
to start with, classically, let's say qualify it classically.
yeah.
Classically speaking, this is
Okay.
a constant.
Excuse me.
Okay, but
Yeah.
yeah, but it does change under quantum relativity effects. If you consider
Oh, okay, yeah.
photographic effects.
Okay, that's fair enough. So, okay, so interesting. So you're using this charge mass thing. I mean, it's an interesting concept. And so it's just sort of an intuition you have that this is going to bear some fruit, or because why are you doing it, or is it just sort of
Okay.
intuitive?
Yeah. So how can we use this particle thing to figure out whether graviton can exist? So if we know about fermions, it's well
Yeah.
known, and the standard model, everything, and then let's see everything is plotting that, and the Higgs boson, they have found
Yeah.
it.
Okay.
I mean, they are not
I don't think
questionable.
we need to debate like whether fermions exist or not. I think we'll just accept that.
Yeah, yeah. Right now we have to accept that because that's the only thing we have. The particles, we know electrons exist in the sense that
We
that
got
electric
we got
charge.
bosons and we got fermions,
Yeah,
and that's it, really, isn't it? Well, I suppose unless you
yeah,
want to go into like other more um
yeah.
exotic
Fermions because
particles.
the mass can change. For example, the electron, the muon mass is different from, and the tau mass is different.
Yeah.
Uh,
Okay. But the mass of the mass of the graviton is what? Zero.
well, that's a questionable thing. There are gravitons with mass, and there is massless gravitons and massive gravitons. So,
Well, that's just a theory, isn't it? There's not, but there. Well, it's all kind of theoretical. I agree. But anyway, so
yeah.
you'd kind of have to prove that there's massive gravitons existing, and well, I suppose it depends where you're coming from. But then you've got these massless. So if you have a particle that's got a charge of 1 and a mass of 0, like the photon, or oh no, wait a second. You can correct me if I'm wrong here. Like some
Mhm.
sort of particle with a particular mass and a charge of and no charge. Does that mean
Uh-huh.
its charge is 0? Does that come out at infinity, or how does that work?
Yeah, so that's a very good, excellent question, Christopher. So
Oh,
the question is, if the gravitons have zero mass, it means ERM is infinite. I mean, you get the value ERM as infinite.
well, wait a second.
Uh,
Does the graviton have charge?
Graviton does not have normally, yeah, it's chargeless. So, so those are the questions. So, what is
But
happening
what
is,
about the
yeah,
photon? Like the photon has a charge, obviously, doesn't it? It's 1
yeah.
or
So
okay.
it will be in the
So
zero line,
that would
you
be
know.
infinite. Is that so? Where is that on your graph? Is that do you have the photon?
Yeah, so the charge is zero, so it will be along this line, the x-axis,
Oh,
right?
Rajan, I can't see that. I don't know why. I can only see
Oh,
your.
can you see what I'm pointing now?
Well, I can see a different slide. It's spin spectroscopy
Yeah.
beyond axiomatic logic via rank 6.
Oh, so it's not okay. Sorry, but you cannot see this slide. Okay, so I have to
Well,
let
you
me
just
go
yeah, if
back.
you just get out of that and then just navigate to the slide on the main screen. Then
Yeah. See, I
it's
cannot.
that's fair enough. Just
Okay.
just go straight to the slide. Then I think whatever slide 5 is it or
So let me see.
10?
Is it showing anything?
Oh, yeah, there it is. Okay,
Yeah, okay.
so it is a little bit small. You've got a photon there, and it's beige or something. So that's the top one. So it's coming out at
Yeah.
1. So why is that on the y-axis? Should that not
This
be
is
infinite?
the bosons are one, right? Bosons are spin one.
Oh,
This is a
that's
boson.
not 1 though. That line there is 1.5, isn't it?
No, this is one.
Oh, okay, so you're looking at something else, but on the image I'm looking at, 1 would be like to your left or something. Oh
Oh,
yeah,
here is point 0.5. It's point
yeah.
0.5.
So it's different. Whatever image you're looking at is kind of different to our image, I think.
Oh,
Because the 0.5 one is pointing down. The one that your mouse cursor is pointing at now is
yeah.
pointing up. It's at 1. So there's some
Oh, there are two of them.
alignment
Okay.
between what you're looking at on screen and what I'm seeing.
I see. Yeah.
Okay, so I
I
wouldn't
don't know
worry
why
about
there
that.
are two.
But just let's just communicate on a basic level about what we're looking at. Your photon is the topmost point there, and on the y-axis, it has a value of 1. Should it not have a value of infinity?
Yeah. So this is the one you are talking about. Is it okay?
Yep. Yes, that's it.
Okay. So that's one. And now
Okay, so
the
why is it
idea
1?
is,
Did you normalize everything or something? But obviously not, because if
yeah,
you did, then everything would be absolutely tiny. So okay,
yeah,
so Rajan, I'm not sure really. Also, it looks like you've got the graviton in there, but it's hidden behind the legend, which is quite
yeah,
substantially
exactly.
big.
Yes,
So
it's somewhere here. It's somewhere
it
here.
yeah, it's at 2 and it's at 0. So okay, yeah. So I don't know. Like, do you want to say something about this?
Yeah. So the idea is that we can actually, we have enough data, but we may have to redo some of it. We can get this in any of these LHC or even tabletop thing for fermions and the for fermions as well as the bosons.
uh,
We can get this value,
yeah.
and we may already have it. Some of it are pulled from there, but we may have to, what you call as the, uh, you have to redo some of the things
Uh-huh.
to this level, and
Okay,
uh,
yeah. So it
but
sounds like
essentially we
you've got a few more. You've got some further work to do on this then.
yes. So the new paper I tell how we can design experiment. What kind of experiments. I mean, I'm not going to detail what kind of experiments will help to do this one. And I when I researched that again, I had to maybe make a few more publications. I have some results, but again, I had to do more literature survey. When I went through some of it, people have done very similar things. Not exactly this one. So they have already data, but this data is, we have to reformulate the data itself to uh, to get the data for this one. So those are things we have to do, but there is some data available for the fermions and bosons, how this EORM and the quantum relativity effect, how it changes the EORM ratio. So we have this data available. What this will help is when you plot on this type of graphing, spin spectroscopy graphing, uh, we can we know that we can extend then that result to the spin 2, which is the boson,
Well, hang
and
on. How
see.
how is it spectroscopic? Because is there any
uh,
actual spectroscopy involved here?
yeah, the spins are the ones that's changing the EORM. The spin is changing the EORM ratio
Okay, but how
in this
does
case.
sorry, what's your definition of spectroscopic then?
Spectroscopy is something that, for example, normal spectroscopy, you change the frequency and see how the intensity changes, right? Or
Oh,
or
okay.
or wavelength versus the intensity. That's a normal spectroscopy.
Oh, okay.
Uh, the optical things.
Yeah.
If you change the light, the nature of the light, then you get that, and also polarization, things like that.
Oh,
So that's a normal spectroscopy. We use that to figure out, for example, X-ray spectroscopy, for example, to find out the elements. For example, chromium or iron, they will produce
yeah, I know about
different.
that. Yeah. So that's
That's
fine.
chemistry.
So
Yeah.
you're making an analogy between that and this E over
Yeah.
M as a kind of a wavelength frequency,
Yes.
which can be then yeah, it's interesting. It's kind of a weird idea. It's good.
Well,
It's
yeah.
good
It takes a
mixing of
while to.
different things.
Yeah.
Although I suppose because of the way the nature of the spins are so quantized, aren't they? That the result in your graph is a little bit. It's kind of a bit boring. Sorry, you know what I mean? It's just very linear. Like it's like all very.
Yeah, because these things are not, we have to, in any of these, I have done very similar thing in my model, IPC model I did. And again, it was showing linear things and line. So how to, you have to massage this data or change the data in order to amplify certain part. Like we may have to amplify this result and replot it, some other slightly change these are very fundamental parameters, right? What I did in the other ones is change it to functional things. So we can change. This is a raw plot, but you can change, you can massage this, and then find the algorithm that will change that, and then we'll start getting curves or straight line or statistical things. So if
Right.
you measure, we get many data, right? Then we have to plot the data and see the trend lines, things like that. So that's a statistical, treatment we have to give for any data, because when you put actual data, they are
Yeah.
all
Well,
over the place,
there's
right?
no there's no trend line in that data.
Not in
Obviously.
this one, but we replot it to change the EORM and find what is the connection, what is the physics behind this. So we have to figure out the
Yeah,
algorithm.
but I mean, if you
The
change it, then I don't know. That sounds like how are you gonna justify a change like that? Seems.
Yeah, I mean, after our measurements, when we do measurements, then we won't see plot like that. We'll see many things scattered, scattered plot. We get a scattered plot, and here also you get a scattered plot. So this
Oh, okay.
scattered
We're gonna
plot,
get some sort of scatters.
yeah. So how do you do statistical processing?
Uh,
Processing
oh
the
yeah, yeah,
statistical plot.
yeah,
We have to
yeah.
do all
But I
those
mean,
things. Yeah.
like, what's gonna change? Yeah. Well, I mean, you'd really have to either do that or it sounds a bit maybe a bit too early to comment on that if you don't have the
Yeah. No. This is the initial
because like
thing.
there's no point in talking about something if you don't have it there. You wouldn't write like if you were writing a paper or something and you started talking about something that in the paper that wasn't in the paper, then do you know what I mean? Or it
Uh,
wasn't referenced somewhere else, then you just have to delete that unless you're saying oh like future work. But even so, yeah, I don't know. I kind of need to in order to talk about it or whatever you need to actually have the thing there.
I mean, this is the extrapolation of the theory to experimental design.
Yeah.
I specify that it's not an actual experiment; it's experimental design. But that's the first step, right? The first step is experimental design,
Yeah,
and
yeah. I
now,
just think this research might be a little bit too in its early phases to really
yeah,
say too much. But I know what you mean. Like I've spent a lot of kind of time working with finite groups, and
uh-huh.
which is a bit like what you've got here. You've got these kind of finite things, and I was always messing around, and yeah. So I've kind of gone back over a lot of that. My idea with the finite groups, like let's say I was using SL2C or something like that,
Uh-huh.
and
Uh-huh.
so that only maps into itself in certain kind of ways. But then I was thinking you could extrapolate that to so it's a subset of SU2 or something, and then you could just interpolate between the different ones to get other types of
Uh-huh.
rotations or something. But
Yeah,
it
yeah.
turns so that's why like if you look you, you know the research I did an entire sort of talk on the 120 cell
Uh-huh. Yeah.
theory of everything in quotation marks here. uh, Looking at that a bit more, I've realized that well I mean there's a couple of major problems with it. Um, so I was looking at a lot of these finite groups, like the symmetric group 5 and
Hmm.
symmetric group 6, which I was
Okay.
thinking might unify everything or whatever.
Okay.
And now the more I look at that, I mean, they're very, they're obviously finite groups. But if you want to do anything like real, like perturbations of particles or whatever from
Uh-huh.
gravity waves or whatever, then you need a continuous group, which is obviously infinite in size.
Uh,
So this whole thing about working with finite groups, I mean, it's fine if you want to do some sort of quantized thing, but it's not really that general, is it? And so it seems a bit ludicrous then to talk about, a theory of everything that's unified based on some finite group with only like maybe 720 elements or something. It's a bit ridiculous. So I think that research is kind of, yeah, it's just, it's not exactly, it's not exactly right. I think it might hint at something that's true, but um, but then it's just you're just kind of in the realm of imagination, Oh, what if
mm,
this is true or it leads somewhere? But it doesn't actually say anything concrete or anything like that. So I just thought I'd give a correction to that here. I don't know what. Maybe I should possibly write a correction under the video to say that it's not the research isn't correct or something. In
yeah.
terms
So,
of the group theory part, I think it's stretching a bit. So
uh-huh.
more recently, I've tried to extend things to more continuous groups, and
Mm,
that's okay. I mean, you get into these kind of thing with loop quantum gravity and and all of this stuff, and then it just goes on and on because it's a very big area of study. You need to like,
oh, yeah.
yeah. So really, I was sort of messing around in the sandpit of like finite groups for a long time, but I think it was a good sort of preparatory step for something potentially bigger, like continuous groups, and really extending that model um, more, like further, and maybe even moving away a bit from the 120 cell into different types of lattices. So it's interesting, and the research could be good. Some of it's a bit speculative, but um, when I'm a bit for when I've got a bit more extra time, maybe from the PhD, I'll
Mm,
return to that. But I doubt. I've sent a couple of papers off to be published, and I would have gotten like just a lot of rejections on the physics kind of part. So
mm,
yeah, so the improved research is a lot better, but I would
mm.
still imagine that it's not like even like if I produce something in the next
Uh-huh.
4 months, let's say I get some time to spend and I produce a piece of research and I'm like, okay, I'm kind of happy with that. Then I'd send it off. I'd still say it probably wouldn't be at the standard needed for any kind of publication, So even though what I'm doing would be fairly theoretical, but that doesn't really matter. So I'd say it could take a longer time. I'd probably need to work at it for a year and or more. Who knows?
Mhm.
So
Oh, yeah. I mean, these things take time.
yeah. So that's it. Yeah. So I don't really have anything to show. I unless I wanted to go through and just point out the things that are wrong. But I think I gave a basic overview there, just so that because like I would have been sort of following, yeah. Anyway, other people's research, and then but not fully understanding how it connected to the continuous thing. I was like, oh well, that just sorts itself out. But yeah, it kind of does. It kind of doesn't. So Yeah, at the moment I'm working on some simulations where
Uh-huh.
you can basically it's a bit because the research is so, how to say, it's in progress. So there's a lot of different moving parts to it, and they're kind of constantly shifting. But essentially, you have this lattice, and then if you modify the theta value, which is the tiling number of the lattice, then you get effects that are abstractly related to curvature. And I say because it's in a hyperbolic space, the lattice, but we're not changing the curvature of the lattice. We're just changing the tiling number.
Hmm.
And then we have a um, so we have a sorry, a pentagonal lattice in 2 dimensions, let's say, to keep it simple. And then we have the dual lattice of that. And then so
Hmm.
around the vertices of those, we will have these like tori. And then around the tori, you have these helical spirals. Well, one around each torus, yeah. And then as you increase the tiling number, you increase the number of domains around the torus. And then
Hmm.
you take one domain and you say that domain is like, I don't know, like a Planck length or some, or let's say two, I don't know, 0 point, or like e to the minus 9, 0.2 e to the minus 9. Sorry, I can barely talk. Something like
Okay,
that.
literally.
It's very small, these like domains. And then as the torus rotates around the vertex, and then you just monitor it from one of these domains, and you check each time and say, well, where is the peak of the helix? And then so you can use that to describe the uncertainty in the waveform, or whatever. And then you could use like a tangent. There's a couple of things that aren't fully worked out, but let's say you could use the tangent, or yeah. So you have the speed, and then you also have, as you increase the tiling number, then the sides of the pentagonal lattice become more and more curved, which you can then use
Hmm.
as a sort of an SU2 um, simplified version for holonomy perturbations from you know from the gravity side of things on the quantum end. And then so all of this, also then you might be able to do like a mass thing with the helix around the torus. You can also vary the size of the torus as curvature increases, and there's a lot of different stuff you could do. You can look at how the area of the torus as it grows could be related to the uncertainty principle.
Hmm.
Is there any other stuff? Um, uh, you know, uh, and then it can relate back to the more finite group stuff that I did with trying to place the particles on the actual uh,
Hmm.
grid. And then finally, there's this issue with like, so if the torus moves at a certain speed around vertex with a certain curvature, then it either is in a stable orbit, or you could say it's going to be in an escape velocity, and so on and so forth. But it seems like at that point, all of these lattice, they'll just describe basically like one particle in the universe, but it extends
Hmm.
to infinity. And then, so if you wanted another particle, you would, in the system, you'd need to create another whole um, lattice. It's a bit like
Oh.
spaces in that way, although
Hmm.
they'd be adding extra dimensions, so it's still in the same. So that's kind of a major thing that needs to be worked out. Is there anything? There's a bunch of other stuff that connects to this, and is relevant. But I don't know. Are you following along with that so far, or do you?
Yeah. So I saw your the one the simulation that you showed in the research gate, and you say that you can get a unification, kind of a first level unification or something.
Oh
You
yeah.
had a recent one, right?
Oh
Research
yeah.
gate. You.
Well, I can share that if you will. I bring
Yeah.
that up.
I will. Let me get off this now. 1 minute.
Okay. Yeah, we'll look at that because well, that is actually different research, but yeah, we can look at that. Um,
Okay.
okay. So it's been a while since we've been presenting any research really on here
Yeah.
or sharing anything. So let's see how this goes.
Okay.
I want to present. Looks like they've changed
Yeah.
things up a bit. Share.
Yeah. There is a little bit change in the StreamYard, but I think they have put more things, more features, kind of
They
thing.
did, yeah.
But
So when I initially like signed in, I was like a bit confused from the. There was a lot of clutter, kind of. But you can just like move them all away, so it's fine. Um, although, yeah, that's not a problem. Okay, let's get back to this. So this is the one you're talking about, is it, Rajan?
yeah, it's the most recent one, right? Unified, yeah.
Oh
CEO
yes, it
output.
is. I need to fix up these tables a bit. So it's something I'm working on. So yeah. So the concept here is so I think the images really are the best thing to help
Uh-huh.
understand. That's kind of the way I work with things. So
Yeah.
essentially, here we have a wireframe of a hypersphere.
Uh-huh.
So the blue lines are meridians, red lines are hypermeridians, and then I think it's something like that. Oh yeah, parallels, meridian. The greens are the hypermeridians. So the concept here is we have like blue lines being the
Mhm.
magnetic field
Ah, okay.
lines, and then the red ones are equally also a kind of magnetic one, and then the
Mm.
green ones are ring currents. So this is meant to be moving towards a model of the Earth's geomagnetic field or any geomagnetic field. Um,
Mm.
so you see, you have it here in more kind of technical language that this is a stereographic projection of S3, so a sphere, a three sphere, which is a 4D sphere, essentially. Um, yeah, and these are just different angles of the same thing, really. So the concept is if the if a four-dimensional sphere can be kind of thought of as a quaternion algebra, which it is, so you can map the coordinates of the hyperdimensional sphere to the quaternions. W is the scalar part, and then these are the imaginary part. So my thinking was that originally the equations for Maxwell's electromagnetism were done in quaternion form, you know?
Mhm.
There's all sorts of people saying, oh, like we're missing a dimension or whatever. But
Yeah.
if so the quaternions as they are here and whatever map directly to Maxwell's final formulation of the equations, which are more kind of abstract. So
Mhm.
that implies then that the geometry of this object here can map directly to those equations as well.
Only
So,
magnetic, right? Not electric field. Only magnetic field.
well, no, there's yes, technically, but there's more to it because you have the divergence here, and if
Ah,
you
yeah.
take it down, see this. So this is
Ah.
these are lines that are diverging from a point at infinity in 4D space,
Ah.
projected into 3D space. So you can
Mm.
so these are the divergent lines, and then you can just superimpose them on the hypersphere field lines, and then you can get like these this this sort of vector quantity, which gives you these arrows. So this is technically then the
Oh, okay.
unified field structure,
Oh, yeah, that's electromagnetic field. Okay.
right? Because the arrows pointing out show the electric field, and the arrows
No.
pointing 90 degrees like are the magnetic. So that's kind of a
Okay.
unified thing. However, I'm not sure if this is completely correct, because if you look
Mhm.
at these loops here, the smaller red loops,
Yeah.
I mean, and then we look at this arrow, for example, it seems to
Mhm.
be pointing away, like it should be pointing up this way, I think, or
Hmm.
down. It's going in the wrong direction. This one's
Is it
fine.
do you saw a pointing vector or something like that? Pointing
No,
vectors?
like I don't think this is necessarily exactly right. I think there's some problems with the equations here, which is probably
Huh?
why this paper, like ultimately, well, it got rejected anyway
Oh. Oh,
from
you
the,
send out
huh?
to a magazine. Did you send out to a journal? This one?
Yeah, I did. They
Did,
actually they got back. I think they said this wasn't relevant. It was out of scope of
oh,
the journal.
oh.
So, but I still think, like you said, this is probably the best thing I've done in terms of,
Mhm.
like, I don't
Putting
know how
together
it
everything.
connects back to what, how would you say, like conventional
Yeah.
physics,
Physics.
like work that people recognize, sort of, rather than
Uh,
messing around with like some weird stuff, but with the
speculative
finite
things.
groups.
I mean, only they think it's still speculative, but I think it is more, you are
Yeah,
just advancing to the next level.
yeah. I mean, I think I think this could be right. I mean, obviously, there are problems here. Um, I'm just wondering, like, has someone else done this? Uh, yeah. Anyway, so this can be extended further, because it's meant to be, it's meant to show the Earth's geomagnetic field at
Yeah.
some point. That's the ultimate goal, is a model of that. So maybe they're saying this is out of scope for the journal because of that. Like, maybe I should go to a more geophysics journal.
Uh-huh.
I really don't know. I would have thought, like,
Yeah.
there'd be no problem, but I think there are issues with some of the equations here. Maybe this one, or this scalar field strength is defined. I
Yeah.
think that might be wrong. I don't think you should reject a paper over like one equation maybe being a bit wrong.
Yeah.
But
Actually,
anyway, that's just me.
the E plus B, you cannot add the magnetic field thing. You have to have I or something like E
Oh, okay,
plus
yeah,
IB or something. E
yeah.
plus I, yeah, modulus thing. So because they are complex, uh,
Oh,
it's a
but are
complex
they complex
variable.
at this point? We projected it. I don't know. See, that's a good point, Rajan.
Yeah.
There's another equation that I'm supposed to use in place of this, but I think it's just, as a maybe a placeholder for something more correct, and that gives the quaternionic rotate. No, so that's the field component. Compute. Yeah. So I think that's why this is wrong then, maybe.
Mm.
So that's good. So if we, yeah, there it is again. So if we can fix that, that might fix these.
All you have to add is an I before the B, the
Right.
modulus
Okay.
B.
Right.
Put an
That might
I
be
which
one.
is
There could be another more. So like this, the field strength.
yeah,
E.
that's modulus. Then you scalarize that. So E plus IB, and then find the scalar value of that E plus
Yeah.
IB. So
So like
scalar
that.
value of F, you have to
Yeah.
find the modulus of F. What that will, you have to compute that
Oh, okay.
instead of yeah.
Well, that's cool. So I mean, yeah. Um, if you want to, I can send you on the code for this as well, Rajan. If you want to
Okay.
fix some
Yeah,
of
I'll
these
try that.
problems.
Yeah, I will do that and then put it in chat GPT, find out whether that's correct. I mean, that's one way AI,
Well, to be quite
ChatGPT can
honest with
check
you,
for us.
yeah, I use
It cannot do. It doesn't do a good job of directly converting it. We cannot just use, oh, do this. Then it does not do that well. But initially, you have to do something. Then it will look at and say, okay, whether it's correct, and then you'll correct it. So it can be used
yeah. Well, I
very
mean,
carefully. The two.
yeah. Well, that's it. I mean, you know, I think you'd probably be, you'd have a better idea of like just on the you probably pick out things that are wrong in this faster than I would.
Yeah. The
So
reason is I
yeah,
worked with initially when I started working with Emmanuel. He's a electrical right? He's electronics thing. So he knows all that. So he wanted me to do that. So how we got interested, and we got interested because I said that then you have to find the field lines, which is a very very difficult, a very tortuous thing we have to do, right? But
really, yeah,
I said, to actually solve it, we have to go through the whole thing, which will take forever.
mm.
But maybe I'll go back, and if you put in the chat GPT, but it can do because it needs lot of the field lines going this way. You are really mapping out the whole thing,
Well, that's
the
kind of
whole
what we're
field
doing
lines.
here. Like, see the results here, and this again is like, what is
Mhm.
that? So that the module. What's that called again? The normed
It's
value or
called the
whatever. Yeah,
absolute value or modulus. Yeah.
yeah. So this is wrong, but I think it's just it's good from a just a toy model, which is all that this is really.
Uh-huh.
So you see it here as a at angle 0, so there's no rotation involved, and then
Yeah.
as we up the torque, so like let's say we have a value from the I don't know the KP index or the solar wind or solar velocity or solar wind density. And then so we up those values, which increases the angle of rotation, and that distorts
Huh.
the field. And the specific behavior that we're interested in for the Earth's geomagnetic field is this concept of magnetic field line reconnection. So we'll have a field line on this side. So here's the day side magnetosphere current. Here's the night side one. And then this line is going to break apart and go over the top of the Earth's pole, if you like, and then reconnect on
Mm.
the night side to create the night side current. Yes, and
Mm.
then we can also obviously with specific what do you call that projections from the 4D space,
Mm.
the 3D space. You see, we can create um,
Mm.
these kind of extended where so this is the bow shock, the sun is over here, and then this is where the magnetic field lines get blown out much bigger on the night side, and then they reconnect to create this green line. Then is the ring current, and this is the day side ring current, and then there's lots of other ring currents inside the Earth as well. You can see them there. And so the idea is that I find all of these equations of Maxwell's, now they are pretty simple in a way, but I think they get very complicated. And especially when you're applying it to the Earth's magnetic field with this, I think the current kind of model is the physical model is the magneto hydrodynamic,
Mhm.
models, which is mentioned up here, MHD sort of thing. Like, yeah, I got that right. So I find it very complicated. So I'm more interested in geometric solutions that might be simpler, and then we could build a model off that. So so I kind of I understand how that
Essentially,
fermions, and I know that
the
fermions relate to Maxwell's equations. So that's why I try and make it. I try. how then we can start applying Maxwell's equations to this structure, and you can see here. So the B field are the closed loops;
Mm.
they correspond to the imaginary part, and the Maxwell
Yeah.
length is this, which is kind of obvious, right? I mean, it's
Yeah.
obviously that it will be the curl, and I
Yeah.
believe these equations look correct to me. So it's pretty straightforward. It's also fairly simple at this stage. Then
Yeah.
we have like sort of more complicated. Quite quickly we can create fairly complicated graphs of the Earth's potentially models of the Earth's geomagnetic field under like stress of solar wind. So here the solar wind's getting stronger. But you see what happens here, it's a bit odd because if it gets too strong, basically it's saying that the entire magnetic field can sort of invert and turn into this donut shape inside the Earth.
Mm.
But at the same time, another one then sort of so it's like a Clifford torus. I guess
Mm-hmm.
we only have the hypermeridians here and some of the other meridians, but if you had the red ones, the red one at this point would, I believe, turn into a different torus. So the issue there is that this is a rotation in 4D space that would be somehow forbidden. Let's say, I'm just spitballing here, I guess, but maybe at like low energies. So if we were to imagine like what would happen now, this could be totally wrong, and you can correct me. Probably is like, let's say you have a magnetic field here that's being generated by an electric field somehow, like a
Mm-hmm.
like a photon, yeah. So this is where it gets a bit
Yeah,
weird.
I mean that's why I say the solar photons change these electromagnetic fields in some ways, right? That's
Well, no, I'm
it's like
just saying, like,
the day and the night.
let's say
Okay.
this is the electromagnetic field of some particle, this blue
Okay.
thing, not of the Earth. And then let's say the particle is traveling at closer and closer to the speed of light, and then it reaches the speed of light. So it's somehow rotated now in four-dimensional space, like
Uh-huh.
not space time, but actually 4D space, I think. Yeah, it should be. And that rotation will distort not the geomagnetic, the magnetic field into this. So
Mm.
this is what a magnetic field looks like from another vantage point in four-dimensional space, which I find
Mm.
interesting. And so, in a sense, then, what if, and right, that these field lines are very circular, aren't they? Which it generally
Mm.
is like the I guess it's like the unified field between the magnetic and the divergent field creates rotation, doesn't it? So
Yeah, yeah.
yeah, so you can think of this as like this could be the a model of the photon then, and that the photon really is just a distorted magnetic field or something like that. But anyway, that's very speculative, but I think it's fun to think about. I don't know. Does that make
No,
sense?
it's a looping. It's like the magnetic field loops and then creates a photon, something like that.
Yeah. It's like you've distorted the field in such a way, and
That it
obviously
can enclosure,
the
create an
elect-
enclosure type thing.
yeah,
You
it's like
don't.
it's weirdly warped, and yeah, so it's a fun idea, I think, and
Yeah,
maybe
yeah.
maybe if it's like very
I'm
strong,
thinking about similar way. I was thinking about
yeah,
similar way at
yeah,
different times. Yeah.
absolutely. So I mean, I think these are ideas that have been knocking around probably in people's heads
Yeah.
for a long time, and uh, but as far as I know, I've never seen anyone actually visualize it or
Because the actual details are very tortuous,
yeah.
very detailed and tortuous. Because you have to worry
You know
about
what it
the
reminds me of,
micro aspects.
Rajan? You know what it reminds me a bit of is these tokamak
Yeah.
experiments, the plasma torus.
Plasma.
It's like, is it fusion experiments, or it's definitely, it's where they're trying to generate, like, basically make a star on the Earth. So they
It's a fusion process of
fusion
the.
reactor, yeah, I guess, or is it fission or fusion? It's I should
No,
know this, but
the magnetic enclosure is a fusion. The fission.
right, yes.
No.
Okay, so there's the yeah, there's a couple of different ones. There's the Wendelstein as well. Anyway, I'm always getting confused between the fission and it should be fusion, yeah, because
No,
fission
fission. Yeah, fission is like
the
uranium,
more
things like that.
nuclear one that we get from the atomic
Yeah,
bombs.
yeah.
Okay, so imagine then that there's some sort of plasma in this magnetic field that's being constrained, and then also you've got the kind of what would you call it, the string theory model, like, because this is obviously very small, so you've got a loop here in string theory. So that's
so
kind
you get a, let's say it's open loop magnetic field creates a closed loop magnetic field kind of thing. Yeah.
Right. So you're saying here is open and down here is the closed one.
Yeah.
Right. So I don't think, like, so this being some sort of, so like if you were to take the Earth, yeah, and accelerate it to the speed of light, assuming obviously it would all disintegrate, but assuming it could withstand such a thing, I'm suggesting that its geomagnetic field would morph into this shape. But obviously I think it's better, and to
quite possible. It's quite possible.
It makes more sense to talk about it on a quantum scale, doesn't it? And say that this is actually.
Yeah, when I visualize it, it makes sense. I mean, it is possible. We have to calculate it, but I think it's a very good possibility.
Cool. And then I think then as you keep going, if you were to keep rotating, meaning keep traveling faster and faster, it would just
quantum relativity
and look like this again, which is equivalent to it not moving.
Goes back.
Yeah.
So it kind of inverts again, you mean?
It inverts again and therefore slows down. And I think you remember I've already kind of talked a lot about that what is it? Twice the speed of light is equivalent to 0 the speed of light. You know what I mean?
Well, so as it initially it will try to form this closed loop, but as it inverts, then it again becomes open like open strings.
Yes, exactly. This we just
at some point, at some critical point.
Yeah, so
possible.
The critical point
those make sense to
be
me.
A rotation angle of like 2 pi or 4 pi or whatever. 2 pi, I guess.
Yeah.
Okay, so right, we can skip this because I don't think that's too important. And there's the proper equation, kind of. And then this problem here probably. But so yeah, so I think this is quite basic stuff. And then we have that. Just want to get to right. So getting back to this. So like you were saying with Manuel, where you're trying to get these field lines, you want to get beyond some kind of toy model, which I do as well, and get into something a bit more reality based. So I think for the future of this project was to basically apply this toy model to actual real world data. So, I mean, I don't think we're going to attempt that today or anything, but the concept is that we would generate let's say you have a sphere and you put spherical harmonics on the sphere, and then you multiply the field lines, so the meridians and on the sphere by the spherical harmonics, and that should distort them so that they go into line with your harmonics on the sphere. And since a lot of geomagnetic models of the Earth's field, obviously magnetic field, are based on these spherical harmonic models, then we can just take this projected meridian lines, multiply it by the spherical harmonic models, and then um, apply the KP index or the DST index or what all of them, the solar wind density and all of that, a photon density, apply those as a torque to the rotation, and then run that as a run the whole thing as like an animation simulation. And what would result should be a reasonably complicated model of the Earth's geomagnetic field with minimal mathematical input, if you know what I mean, compared to something like MHD. So that's really the goal here, something that's very intuitive. Like, I think like pretty much anyone can understand what I'm getting at here. It's fairly straightforward.
Yeah, sounds good. Yeah, that's good project.
The question is, though, does it really produce? Will it produce what we're looking for? I think it probably will to an extent. There will be some good outcomes. The question is, I mean, even here, like I'm wondering, okay, you have this line. Look at how big this is. So this is obviously in the process of expanding and breaking somehow under the solar wind, but the idea that it would move out towards the sun to do that doesn't seem right to me,
Well, when you correct the equation, maybe with the actual finding the scalar field, you have to correct the equation, right? Maybe it'll take care of that. I mean, in the sense
No, I
that
don't think
it
it
will
will,
probably
though,
involute.
the scalar
I think it
field.
will involute. It won't go out, but it'll go back into the earth because of gravitational effect, whatever you call it.
Yeah, there's no
So
gravity in this model, though. So
yeah. So
the
when you
scalar
add
field,
gravity,
the
when
scalar
you add
field
gravity,
here.
yeah.
Sorry, Rajan. The scalar field
So
here, it is the color that you see in the diagram. Yeah.
okay.
So it's much stronger towards the center of the Earth, and then you have this this field line. This is the North Pole, obviously, and then it's just weaker as it goes out. So it's supposed to weaken at whatever 1 divided by r squared, or 1 or cube. Some people say for the.
Yeah.
So
I'm sorry to yeah.
that's fine. So the question is, so we're only, if you look here, we're scalar field rotation angle 2.82, then we have 303, and then obviously there's some critical value that's crossed between 3.03 and 3.25, where this field line flips over the top and then reconnects here. But and then it goes up to angle 3.4. And then you see that's kind of it, though, because now you're stuck. You can rotate back, okay, but that's going to be non-physical because obviously the field lines don't reconnect back towards the sun. But what you could do then is to split this field line and move it out back into, so that it moves in here and then pushes one of these further up, and then that one flips over. But that all seems very, what's the word? It just seems a little bit contrived. You'd have to actually go in and fit these mechanics into it, and it becomes very annoying. What I would prefer would be some other rotation, maybe of the hypersphere, which just produces the effect that we want. And I'm guessing that exists, but I don't know what it is or how to find it yet. And it might not exist. So, although it should, but who knows? So,
Yeah.
and then this
I'm sorry too.
Really, where it's hard for I'm guessing that this field line does flip over the top, because if it does, I mean, that's exactly the kind of thing. But on the other hand, No, yeah. So I was worried that it didn't flip over, and that instead what we were seeing was maybe this one expanding on the back side and this one contracting on the front side. So it's like a fake expansion. But I believe that is correct because, well, I was worried because what are we getting up to here? Rotation angle 3.47. Now, presumably that's in radians, right? Oh, gosh. Rotation angles. I would say it's in radians, right?
Yeah, it should be. Yeah, yeah, that makes sense because that would be too small. I mean, the one
Well, it's
thing.
obviously not in
Sorry
degrees.
to
Yeah, it's obviously
um,
not in degrees.
the eccentricity. You have to consider the eccentricity of the
Yeah,
axis So it is tilted in some way. And also these lines are like three-dimensional. It goes like this, like this, like this.
uh-huh.
So it is, it is looping into the sphere,
Yeah,
in all the different sides. So if
yeah,
it is looping here, so that eccentricity is putting it here, and the looping changes, then you see that how the minute changes in the angle can, and the sun is now coming, the photons are affecting
yeah.
this side. So then it can flip. There's a possibility it can flip, but
Right.
that flip may not be as much as uh, as much as you are shown, but it will start
Well, I
to
mean, that was what I was, yeah, like I say, that's what I was worried about. But so, okay, let's go back up here. Maybe, okay,
the
so like
fractal. Maybe you have to
3.4
consider fractal.
radians is pi radians, right? So
Yeah,
it's a half rotation essentially.
yeah.
Whereas if we go up here, we
Uh-huh.
see, oh, let's get back to this. Oh, you see, this is where things get confusing. This is sequential activation. So that's something we may need, some sort of
Mm.
sequential field to allow for this process of the flipping of the lines where they get pushed out and new ones flip over for the reconnection. So
So
here we
your
get
inversion and flipping, two different things. They are two
possibly,
different,
yeah.
right?
I want to ask you more about the point you made about eccentricity there. I assume we're just
Yeah.
talking about. Well, we'll get to that in a minute. So we've got
Okay.
an XW. So this is a rotation in the fourth dimension spatially. So that's what we're looking for, and it starts at pi rotations, and it keeps going, and we're already at 1 here. So this has gone way beyond. This has gone beyond 2 pi rotations technically, because it's gone
Hmm.
back to 1. So it's a modular loop of radians. So this is suggesting, because I was thinking, like, for this field line here expands, loops over the top, but all of the field lines are now heavily distorted at this angle, which seems to correspond roughly to what we did here. So that's a bit confusing. So I think, but however, so yeah, so however it's occurred anyway. The point is that we're limited to the amount we can rotate in the fourth dimension for some reason in our universe.
Yeah, but the thing is that we have to consider more than 2 pi. We have to consider 4 pi because that's a solid angle, rotation. So
Well,
the
hang
4
on.
pi,
Isn't solid angle to do with some sort of perspective thing or something? Like
no,
the solid angle
it's
on the surface of
a
the Earth is
three-dimensional
doing
thing, right? So
how
it
much
is not a circle.
visible from a particular perspective or something on the surface, like, of the Earth. But yeah, no, it's interesting. But I think, well, 4 pi. Well, hang on a sec. 2 pi is just one rotation. 4 pi is going around twice, right?
No, the solid, like a torus or
Sorry.
something, that will be 4 pi
I,
because it is
no,
more
no,
than a
no.
circle.
More than, yeah, but like, we're just talking about 360 degrees rotation. That's 2 pi.
Okay.
4 pi would be 720 degrees of rotation,
Yeah, that's
which,
solid
as
angle.
we, which, as we said before, will just bring us back to this, because
Okay.
Uh,
Yeah, it
two
could be. Yeah, that's true.
2 pi rotation brings you here, I think. Or no, let's
Yeah.
say
Okay.
sorry, 180 degrees probably brings you here in 40, and then another rotation brings you back to here. I mean, yeah. So
Mhm.
I'll have to look into that, but
Yeah, yeah.
there could be an issue because, but that would suggest there's some, like these lines could switch with these lines or something, the red and the blue, which
Hmm.
does happen. You know, they invert, but
Yeah.
and I assume that takes place after 180 degrees of rotation, because otherwise this would be like a double cover, and I don't think it is. So, so either way, yeah, I mean, maybe you're right. Maybe we should look into that. But the point is that there seems to be like a lot of overhead here because we're not expecting unless the energy is very high and the particle is massless, then we might get to a state like this. But in general, something sitting
Graviton or
here
something.
with a, what?
Like
Yeah,
graviton type thing.
yeah, maybe even that exactly. Like maybe it's that kind of thing. I don't really know. So
Yeah.
maybe, but like with something as big as the Earth,
Mhm.
and maybe with it has a fairly weak magnetic field, you know,
Yes.
compared to something highly energetic. Is it's limited in the amount it can rotate in 4D space, which means
Mhm.
that the amount the magnetic field will distort is also limited, and and that's kind of interesting. So it puts constraints on the system, which are possibly related to general relativistic effects, and and then that kind of gives you a way maybe to unify this with general relativity. So it'd be like a geomagnetic um, or electromagnetic unification with general relativity by way of rotation in 4D space. And like almost, it kind of goes back to oh, can you imagine if we could somehow connect this to that gimbal lock idea, where you try and do like, is it Euler angles of rotation, or SO3 or something has a lock where it can't get past a certain point, um, and and then it only can kind of it can only stick and then rotate around the z axis, but the quaternions can move through that, which means, you know, which allows for this sign flipping, if you like, of the that we saw up here, where the magnetic field becomes a unified field, and then, you know, and another field which maybe was a unified field becomes a magnetic field, and so on and so forth. So there's kind of a it basically, it's like toppling over itself, you know, like a bit of magnetism creates a bit of electromagnetism, creates a bit of magnetism, kind of thing.
Yeah,
So
it's
that's
induction. It's
there.
inductive, right? So inductive processes. Yeah.
Right. So that's exciting. I think. I mean, there's other
Yeah.
stuff from the past that I tried to do, where I was trying to unify, or I was trying to do some kind of thing with 4-dimensional physics. Um, I think it's kind of underused, and it's definitely a fun for spatial dimensional physics, and should be used more. It's a Bellman equation. Oh, this is not going to work. No. What is the EPR? EPR injector? EPR paradox.
Oh,
So
yeah,
this,
EPR, yeah.
yeah, this is
Einstein,
from a good while ago.
Lebowski, yeah. Einstein,
Um,
Lebowski, yeah.
this contains the. I mean,
Ah,
this is quite complicated material here that we're working with to do with the, you know, Bellman equation, and you send it through these different magnets that are aligned in different ways, and Yeah, it, so it gets into a lot of stuff there, but it simplified. Bell's inequality is simple enough when you look at it from this perspective. But and then the issue with polarized lights, and here we get into the Euler angles versus the Quaternion rotations, and with the Euler angles, we see that two of the axes line up, and therefore we get this kind of gimbal
But
lock.
we can get the invariant rotations, right, with Euler.
It would be invariant, but you also get a gimbal lock. So you can
Gimbal, yeah.
actually you can demonstrate this with plenty of programs. So if you're here in 3D, so the point here was if you move from a gimbal locked Euler angle rotation into a 4D sort of rotation, you could account for the kind of things that we observe in these experiments where they appear to be blocked off, but then they they go through a different type of rotation and then they become unlocked again, kind of.
Is it like a polarization type thing? Get polarized?
Yeah, I think it is a polarization experiment from the point of view of whether it's spin up or spin down, but it's pretty low polarization. So I don't think there's a huge amount there. That was sort of but it would be interesting if we could apply that gimbal lock to the new thing. I don't. I mean, you can kind of do that fairly straightforwardly. I think did I try and send this? Oh no, I'm working on a new paper to do with this concept. I don't think this is it. Might be.
You're correcting this one?
Yeah, you see, we have the hypersphere lines here as well. That will need to be corrected with the new hypersphere lines because these were this was the wrong kind.
You are twice the angle or something, the factor of 2 or something. Yeah.
It was a bit weird. It was just going in. Basically, the green meridians are going to have to sit where this kind of yellow sphere is, and then the other meridians will go out. So it'll be interesting to see what the results of that is. But first, we'll need to actually get the proper measurements for the size of the universe, which is still in. It's just haven't gotten around to it yet. I sent this paper off to be published, but they got back and said there's a couple of problems with it. One of the big problems that they had actually was with all of these numbers, the fact that they're correct to so many decimal places. And generally in astronomy, you never get anything that's, when you're dealing with distances that would be correct to such a degree of accuracy. Of course, the model that I'm using allows such high degrees of accuracy because we're measuring the universe, the hypersphere of the universe in relation to the wavelength of the hydrogen element. So, hydrogen alpha or something. So we can get down to those kind of accuracies, but they're so not used to that kind of concept that it, he just didn't understand that. So I'm not sure what to do about that yet. But there's problems here that need to be fixed anyway. Maybe that's getting a bit off point. I mean, that research is so different from anything else we're doing.
I like how I define our project to be quantum cosmology. So on one side we have the quantum, the other one is the cosmological thing.
Yeah,
they're
I really like
some
that.
ways, yeah. That's my the new definition. I mean, the new thrust all together is a quantum cosmology. So
yeah,
I think that will take care of
here's
everything.
the unification paper with the so-called theory of everything that I wanted to correct earlier. Because I was saying, oh yeah, we've got a grand unified theory, we've got a theory of everything where we've solved the problem, but then I'm just looking at this again, going, no, this is wrong. You know, it was a fun exercise, and I think I learned stuff from it. But and I think this part really is opening up into the next iteration of this, if you like, the next version, which is going to have as you increase the tiling number, you get more curvature in this space. So these link complements go to 0, and these other links go to infinity, which is equivalent to space contracting and time dilating and all of this kind of stuff. So it's going to be more interesting as we go on. But I think, well, I like all of this sort of group theoretic stuff. As I mentioned before, it's possibly a bit too finite.
Right.
You know, the groups are too finite would be really useful for more, you know, for bigger kind of how do you say, simulations of particles. But yeah, so again, it's going to be fun to figure it out. But I think this is more on an abstract level. I was always thinking of it that way anyway. That's kind of like the hidden sort of fundamental, rudimentary code from which other things emerge. But I don't know if that's particularly interesting. But we will see, you know.
What I
Yeah,
say is like it's like a pot, very similar to standard model. What they did, put everything into the pot and see what comes out of it. So I think it's not a bad idea to do that. It's like you put all the pieces of puzzle inside. I did that some time ago.
yeah,
Actually, I have a box. I put a lot of the pieces of puzzle. I mean, I wrote down what they are and then put them in the box, and then you see what comes out of it. Uh, and then
yeah,
when you reserve that, I prove that it's a black box universe. That makes more sense because what we are trying to see there is a perspective, and I differentiated between perspective and perception. Perspective is more system related. Perception is more people related. So if you have
right,
perspective, you come up with the system parameters, which means and the perception is assumptions. So perspective, is different. You have like a hypothesis that comes there. So between hypothesis and assumptions. So you're switching between the two and see how
mm,
how it plays out. Because definitely, if we go in the heart of everything, we are assuming something at some point, or we are hypothesizing something at that point. So that's why it becomes speculative, in that logical sense, in the larger sense. See, one of the things I think even Sabine and I found one thing recently, yesterday or today. Uh, First, like we talked about, Sabine talks about these. There is a video talks about how the random fluctuations can become a real thing. How you can create a real thing out of a random fluctuation. That's very similar to our superluminous condensate thing, right? So something is just randomly fluctuating. How can it form this thing, that what we call the particle interface, and the universe, the real observable universe out of that? you know
right,
so was it initially like a random fluctuating thing? So what I found, that physics means there should be something inside that makes it that way, and that could be the monopoles. And that hot PDP mechanism does explain that when at some point the north pole south monopoles come together and they lock up and produce a hot PDP. So that's how you get a localization. And that's still a question. That's That's the fundamental question we still have to answer to realize that, because the random fluctuation, like nebulae, we have, and they observed it. And the recent one I found that the JWST, the James Webb, and the Hubble space agree upon the Hubble constant very closely. And I can pull up that article. There's an article. It's a very interesting article.
Okay, go ahead.
Yeah. So let me. How do I? Okay. Let me.
When you're done with this, I wanna share the more up to date research that I was doing, which I think you'll find interesting. It's quite
Okay. You want me to pull
because
up
like
this
I was
now and
trying to
then?
correct showing the faults with the current model lens. But
Okay.
yeah, you'll see some of the new stuff is pretty wild uh,
Uh,
because we've kind of moved on a lot in the last couple of months with these large language models, and
oh
they
yeah, yeah, yeah.
they
Yeah,
just allow
I
you to like accelerate your work. You do have to be careful though, because like obviously
yeah,
there's issues.
yes, yes,
But
yes.
it's
Mhm.
I don't know. It's a great time, so I'm quite positive on this.
Yeah,
You know, so it'd be interesting to see what other people generate as well. But I'll just show you what I'm doing, and you can have a you know I think you find it interesting. You can have a bit of a laugh with it. Just how quickly you can move to different subjects. Really, I'll
yeah.
have I'll have to find it. So
I
what do
think
you
this is the one.
want to
Okay.
share? An article related?
Yeah, yeah. So let me. I think I want to ensure that's the one. Let me just go through. I think it's the one. Before I put it in the this thing.
Okay.
Where is the allowed?
So is this sorry? Is this
Um,
related to stuff you saw Sabine Hassenfelder's, or is that something else?
No, today is a different. Now
Okay.
I can pull up Hassan Fred, but
No,
this is
no, don't.
more recent.
This, yeah, she's got some good stuff. I mean, she's been doing some
Yeah.
interesting work, but I kind of she's all over the place. So you
Oh
don't need
yeah,
to.
that's true.
There's probably other developments. This is more JWST, is it? With the
Yeah, yeah. So
yeah.
this is more focused. So I think this is the one.
Okay, great.
Um, okay. So okay. So something strange is driving the universe apart, and James Webb just confirmed it. Okay.
Oh,
So
really?
essentially,
Was this a
uh,
dark energy thing?
yeah. So when they are
Okay, well,
looking at
this is a this is
something,
this is bad news for my model if they're correct, because my model doesn't allow for, well, I suppose it does
uh,
allow for it, but it prefers not to have um shouldn't be there. But go on anyway.
okay. So most
That's my
trusted models,
that's my cosmological model now, not the anamorphic
yeah,
perspective cosmology, not the quantum stuff. But go on. So how does it
yeah.
work?
So for the expansion rate, the Hubble
Mhm.
constant doesn't add up. Okay, it's called Hubble tension, right?
Oh yeah, yeah,
Uh, Analyzing ancient cosmic microwave, so CMBR, gives a slower. This gives so lambda cold dark matter, whatever, gives 67 kilometers per second per
right.
mega. That's a thing. But the Cepheid variable, the supernova thing, that gives
Mhm.
73. So this is a
Yes,
hybrid tension because the difference is very high, right?
yeah.
67 versus 73.
And
So this is the whole
it's
thing.
getting wider, wasn't it?
Yeah,
As they started getting more accurate.
yeah.
That was the
So what
worry.
they're saying is that, yeah, the flawed measure, the hope that discrepancy was simply a result of flawed measurements from Hubble space due to overlapping starlight or limitation resolution. That's on table even now. So the Nobel laureate Rice, they did in the JWST, 1,000 Cepheid and five across five galaxies.
Right.
And surprisingly, the results from the thing they match very closely. So what they got was the Webb did 72.6, the Hubble did 72.8, very hardly any difference, right? So which means
Yeah.
it's not a measurement error. It's not a measurement error.
Okay, but
So what
sorry, what are they measuring? Their Cepheids, or are they measuring?
Hubble constant?
I know, but how are they measuring it? Because the Hubble tension is cold dark matter, right?
Yeah.
Gives it's actually been a while since I looked into this. So the one is theoretic, and the other is an actual measurement from the observation. Is it?
Well, both of them use theory to some degree.
Of course, yeah,
They
but
have to use.
one is like based on the redshift of the galaxies and then calculating
Yeah.
the Hubble constant. But that's exactly it. I mean, you can calculate based on my model, the anamorphic perspective model. You can calculate the redshift all you want as accurately as you want all day. But if you plug it into one model, it'll tell you that everything's moving away at this speed.
Ah,
But if you plug it into my model, uh, it just tells you the size, like basically the size of the hypersphere in a way. Well, no,
it
that's
appears
the
like that, but it's not like that. Not necessarily like that.
it doesn't. Yeah,
Actually.
exactly. You could have a different model where it's, I don't know, based on Doppler redshift instead of you know expansion or something. So I don't know if this. I think the headline is a bit of a clickbait. It can't be from my perspective, because it doesn't
Hmm.
definitely doesn't prove their model yet. So that's good
And
news
they're
for me.
saying essentially they're saying there's a missing ingredient, like a early dark energy or something, or strange dark matter property with exotic particles with having that primordial magnetic field. And what they're saying is that essentially they're saying that it opens a door wide open for theoretical physics to get creative. And so we have to come up with a totally different theoretical physics. That's what I'm saying. Theory. So this theory doesn't add up,
So they're
conform
saying
to
that
it.
the problem. It sounds like they've ruled out cold dark matter. Is that it? Lambda cold dark matter as a
Maybe roll
cosmology.
out, but they said it cannot explain that essentially. So essentially, we means you have to modify it or do
They'd have to
something.
modify it. Yeah. Okay. Well, that's
So
interesting because only one of them can be right. So it sounds like
yeah,
they're going more for. Well, one of them was a model, and the other one is just observations. So it sounds like they're just
yeah,
without a model now. But then you
yeah.
were right. You're talking about this basically because they keep finding these stars further and further away, or galaxies, and they're fully formed. That they've had to increase the age of the universe dramatically in order to account for this, or completely change the model for the Big Bang, which is leading towards the idea that we're
Uh-huh.
all inside a black hole, which became very popular.
Yeah,
And also, I mean, that's kind of related to Susskind's
I
work,
like
isn't it?
that idea that
Um,
we could be inside a black hole.
I
Yeah.
don't like it at all. I think it's very good.
You don't like it at all? Yeah.
No, well, like if you look at the anamorphic perspective cosmology model, it's very
Uh,
similar to Suskind's work from he's got everything projected into bulk space from a two-dimensional surface, whereas I've got everything projected from what would you say, like a four-dimensional hypersphere onto a three-dimensional plane, tangent plane. Um, so they're very similar, and you could possibly sort of distort one into the other, but not really. But I mean, the kind of black hole signature in my work would be the what is the word? It's like the
no
projective point,
singularity. You
the
mean
projective
no
point at
singularity?
the
Hmm.
projective point at infinity, where
Hmm.
all of the galaxies converge to this point. But because the density gets lower and lower the further out you go, there will not actually be any what's it called? There won't be any singularity. So Rajan,
Oh.
I'm gonna share the other research that I have.
Okay, okay. Yeah, this is Sabine. We can do it
Oh yeah,
later.
no,
Now
we
I
can get
can.
to that. Yeah. Okay, let's see if I
Let
can
me.
find this. So I did see one of her most recent videos talking about something like a naked singularity or something that they discovered, but
Oh,
I didn't actually watch it. So
I have
um,
not watched that. I think I'm not sure.
yeah, because it's interesting from, I mean, there's something to do with,
Oh, it's like a no hair type thing.
I
Oh
think
no.
it's something to do with, is it the censorship or something?
Ah,
Universal censorship.
yeah. There is something like
Yeah.
that.
Paradox.
That's a landscape. What is it called? It comes from think theory. I think that
I
censorship.
think it's a relativistic thing, if I'm not
Yeah,
mistaken.
I
Because,
heard that term.
yeah. Anyway, so it's one of these big problems in cosmology. I think they ruled out if there's weak and strong censorship or something like that. You can exclude the singularity from the rest of the universe in a weak way or in a strong way. And I think they ruled out the
Yeah,
strong
actually,
way.
yeah.
But
I have a paper
basically the
strong
problem
gravity
is
in.
there's supposed to be no such thing as a weak or as a naked singularity. But then I think she was saying that they might have found one, but I don't even know. I'm not even sure about that. So okay, so you can see that. Great. Um, I'll just sort
Yeah.
of get through this quickly. Now, there's a problem here because initially I was projecting the 120 cell or its dual, the 600 cell, into a 3D hyperbolic space. But there's a problem there because you'll get weird overlaps, you know. So what you have to do is have like an original stereographic projection, which perfectly aligns with the dodecahedral lattice of the three-dimensional hyperbolic space, right? But all of that is a little bit overly complicated anyway, so we want to flatten it down into just a two-dimensional pentagonal tiling on in a hyperbolic two-dimensional hyperbolic space, and that makes things easier. But this is older research, so those are the two problems here. When it's a little
Is it
overly
connected with the Penrose styling? Is it connected? Similar?
yeah, kind of, but not directly. Okay, so we can encode curvature um,
Yeah.
by taking the the Schwarzschild radius
Yeah.
equation, and then we just
Oh, you are converting into polar coordinates. That thing.
um, maybe possibly that probably happens at some point, but basically we have to do some. We take a density law. So theta is the angle
Hmm.
for the tiling. And then as the angle gets smaller, the tiling increases.
Hmm.
And so that's equivalent to as the radius of the black hole gets smaller, the curvature increases. So that's what we
Hmm.
saw earlier, which means the link complements get shorter
Yeah.
and the other links get longer. So um, this is more just the basic mathematics to it. You can couple it to time dilation, and then we're hoping to introduce quantum effects so that it becomes more of a unified space. And there's some of the mathematics and coding behind it, and generalized. So that's just how the equation is formulated. Blah, blah, blah. It's a lot of repetition here. And so these are the graphs. As the dihedral angle gets smaller in radians, the density increases. So basically, we can. Well, yeah. Okay. So there's more equations, but and it shows how as the density increases, time dilation increases along with the dihedral angle. So basically, the idea is that by simply modifying one parameter, we're going to get a whole host of interesting like concordances, both in general relativity and in hopefully in quantum mechanics. But basically, what we do here instead, there's possibly a bit of continuous work here, but I'm still kind of in the realm of the finite groups. And the finite group we're working with here, I think this is actually the 600 cell lattice. It says the 120 cell, but this is probably the 600 cell. So we use SU2 holonomies here on the 600 cell. So we have the vertices as unit quaternions, and then, so you create the SU2 map from the 600 cell vertices, and we get the SU2, and then we generate the holonomies for those. Basically, the perturbations with some sort of quantum gravitational waves, right? Mm. And then we get this kind of results here, which is sort of strange. So this would be the energy density of the vertices in the 600 cell. So this is a nice kind of quantized.
So you are like a cluster at some point. It's clustering.
You'll see now in a minute. I'll probably get more clear as I go on. Hopefully, if the data that I'm looking for is here. So there's just more of this stuff. So this is just refining the model so that it's generalized to all types of masses. We just use the Planck mass to begin with, but this can be scaled for no matter what the mass. You always get the correct curvature for the dihedral angle. And that's basically what all of that is saying. And that as well. So we can skip all of that. Now this is where we get into the holonomies and curvatures. And this is based off the, once again, this basically the 600 cell vertices. So it produces this pattern, and it will always produce that pattern, despite the amount of perturbation, let's say, you put in there, or the amount of curvature or whatever. So this pattern is somehow unique to the 600 cell, possibly. Well, I mean, we'll get into that. Moving on. So these are the deviations, but is there? I'm just looking for something specific. Yeah, maybe this. Yeah, we can get to that then. So these are the holonomy deviations. Now, this has been refined in later work, and it gets a lot steeper, the curve. But we can see how, as you take a loop around the 600 cell, the holonomy deviations from the identity. So basically, as this tiling curvature factor gets bigger, the deviations also get bigger. But I fixed this so it's much more obvious in later research. I'm not entirely sure where that research is at the moment, so I'm not going to go looking for it. But so that's kind of a loop quantum gravity formalism, if you like. And then this is it again, but we have we have like an SU. So this would be an SU2 identity thing, and as we increase the curvature deviation in terms of well, these are in degrees, the holonomy deviations get larger, and here we just have like sort of a random deviation to show you how that works. Now this is going to be interesting because in future what we can do is we can take this. And this kind of relates to some of the research you were interested in, Rajan, over the years. Mm-hmm. We can take this, like, let's say just a random pattern with the deviation, and then we can force on it this kind of, okay, do you know those, quadratic equations with the and you always have this kind of um, like it's related to uh, Pascal's triangle and the way you have the, the coefficients. So like you'll have 1x squared plus
Mhm.
3x plus 1 or something, you know? So it's this kind of sorry, I've kind of forgotten the term. There's a specific term that I'm trying to think of. Um,
Is it like a numerical process? Like you convert x square plus ax plus c or something, and you transfer x square equal to minus, and then you say equal to 0. So you convert that to x square equal to minus of ax plus c, and take the square root, and then you iterate over x to get the value. So it's an iteration process. Is that a one quadratic iteration process or something?
right, yeah, but I think there's a kind of a specific thing where you have you know, so you'd have like two choose three or whatever.
Mhm.
It's kind of uh, it's quadratic.
Like
So you have binomial. That's what I'm thinking of. Binomial. Yeah,
binomial,
where you have a binomial coefficient.
binomial binomial algorithm, or
Right. So you'd have like x plus 1 to the power of 4 or something like that, which would
uh,
give you one of the rows in the Pascal's triangle. And then you'd also, it starts to connect to a lot of other areas,
Fibonacci or something.
areas of mathematics. Yeah. So it's, yeah, the binomial coefficient formula where you have um, this kind of n choose x times p to the x times q to the n minus x. And
Hmm.
yeah, so all of that kind of area will be interesting. And basically what you can do is, and that all connects to then probabilities. And so P is the probability of success in one trial and Q is the complement. And so then we can see how that will relate to the quantum world. And so if you can do that, if you can, well, you can do this because I've done it in the past. I actually have the code for it, but you can take the binomial equations and push it to the limit, whatever that is, the infinity. And what happens is it goes to a flat line, like the holonomy, the perturbations get less and less intense, and then they finally just they flatline. But here, right, this never flat lines, Rajan. It just
Hmm.
the perturbations get so small that they become basically invisible to the eye, but they're still there, right? And
Hmm.
that's the key point that I want to make here, and the one that I think you kind of been bringing this up in the past a lot. I remember where you're talking about what if you take like a sun? I think you were. This might be the example you used. You have a sun, a big burning bulb of hydrogen or whatever it is, and then
Yeah.
I say whatever because of different people's opinions about whether the sun is got. Anyway, we won't get into that. But anyway, there's different theories. So, but if you put that far enough away, it becomes a point, doesn't it? Or something was
Yeah.
your
Yeah, yeah, yeah. Observer physics. I did a couple of PowerPoints on that, and very precise mathematics of that.
right? It's a
Yeah,
perspective
actually, yeah,
idea. And
yeah, perspective. So,
where is so who came up with that? Is it that's
so,
something that
so
people are working on, is it?
yeah,
Or
yeah. So, no. These are very more accurate math I did on that. How see? Suppose you are seeing a hill from far. It looks like when you're driving, right? As you drive towards that, you start seeing more and more features. The
right?
point becomes so you can actually look at. Then you pull back. You can look at the whole thing as a point and
Hmm.
then operate on. Yeah. So you
Yeah,
can
yeah,
still
yeah.
work on. Yeah.
Interesting. So that's what I think. There's a connection here as well. So we would start with the most intense holonomies, and then reduce them down to so it's kind of inverted. Instead of when you get to zero,
Mhm.
you have this flat line. It will be it will be inverted. So it's when you get to infinity, it will flatline, and it will actually be a flat line. Um, and so that could be interesting because then we'll be linking these binomial coefficients directly to holonomy deviations, and therefore directly to general relativity. And the interesting thing about that is that these binomial coefficients are already a part of special relativity, I think. Um, I don't know the details of that, but it's not too complicated. But you can find that information out if you just look it up. Um, I can have a quick look for it here, but no, I don't think. Excuse me. No, I don't think I can lay my hands on that. But anyway, so that could be an interesting thing. That's more of like a connection through mathematics, which is fun, and I think that's something that we need and that we're looking for. But I'll continue on here anyway. But it's something to think about. That at infinity, this will look like a point. Which is what you're talking about.
Yeah.
The chaos becomes a point, but we
Mhm.
know that point at infinity is actually at zero, and that there is still structure in there. So if you have the math, if you have this mathematics, you could apply it directly to that, or if you have some ideas of what to do there, that would be good. Um, who's it was it is that is does that idea come from like Born or someone or
No, I extended the idea. This is my original thing, but
oh, okay, oh
Einstein
great,
was using, many other
synthetic,
scientists were using that. Einstein and everything was using that. If you see anything from
oh
far distance, it will
yeah,
appear like a point. Like that
oh
we see in the night, right? The stars as point, tingling
yeah,
points.
yeah, yeah,
But if you look through a telescope, they have so many features in them, right?
right,
I mean,
okay,
Earth
yeah,
also
great.
will look like that. If we pull away from Earth, like a satellite, we go
Mm,
and we go far into the into the space, then the Earth will appear like a point, right? If we go pull far
that's
enough.
it. That's exactly it. So that's going to be an interesting thing to look into in future. But right now, I want to go back to these to this quantum uh, gravity. No, it's more like a quantum group theoretic uh, quantum gravity, if you will. So this is
Mhm.
not a continuous thing. We're still dealing with the vertices of the 600 cell here. So basically, there's an idea of like you can have some kind of topological action instead of this SU2 holonomy thing, and we have the topology because of the because we're going to relate it to the hyperbolic lattice, which is a big topology sort of lattice, obviously, and this is used a lot. They've tried to bridge um, holonomies and quantum gravity with those kind of lattices. So there's a lot of work done on that, and I think it's quite complicated. I think what's going on here is a much more rudimentary form of that, maybe to the point where it's basically not that great, but we'll see. But I just thought the interesting thing about this was it gave certain results for the you know um, well, it's coming out here as so you have a topological action that comes out as a frequency. Um, so, well, the
Is there a
interesting thing
frequency
is,
of occurrence? Frequency of occurrence or something?
I think it's actual frequency.
Oh,
Right. So I think I can. So it's converted into frequency somehow, possibly using.
I thought
There's
frequency of events.
no.
Frequency of events. No?
I think it might be actual frequency.
Ah,
So if we look at this, the distribution here is a bit like a black body spectrum.
hmm.
If you think about it. So, but
Yeah,
you
it's
have to shift it,
asymmetric. It's asymmetric.
right. You have to
Asymmetric Gaussian. It's not Gaussian, but asymmetric Gaussian.
right. Yeah. So you have to shift it by. You see the way it goes into the negatives here. You have to. That's interesting. I don't know why it does that, but you shift it over by 2 because it all has to be positive for the next step to work. Now, right, and so this is the black body spectrum, and then we try and fit it, which is the blue line. Now, the blue line is going way off the screen here, but this is the best fit that I could get. I think the reason why it doesn't fit properly is because of the scaling issue. So if this, right, so the reason why this becomes frequency is because I'm saying that this is a black body spectrum. Do you get me?
Mhm.
Which means
Yeah.
it has to be frequency, right? And then you have spectral density.
Yeah,
And
that's why Planck came.
this becomes
Planck's thing was
frequency.
this. Yeah.
Right, so this is frequency down here, and this is obviously very high. So it's in the terahertz range. And so
Yeah.
then, because this is a spectral density, or a black body radiation thing, we can start to get into the kind of thermodynamic equations of the quantum mechanical stuff that we're looking at, which is already bridged
Yeah.
with the quantum gravity stuff. What we get is an estimated temperature of like, what is that? 400 billion or 400 million?
Yeah.
42 billion Kelvin. So that's quite high.
Like giga, almost like a giga, close to a giga,
Right.
more than
Yeah.
a billion, more than.
Yes, possibly. So here's nicer. We've got the scientific notation. So that converts to a peak frequency, or no, maybe the peak frequency of the actual Planck fit is like way up, So it's
More
like,
than a gamma. It's a super gamma level.
oh, interesting. And then so you can look at things like energy density and entropy density, but this is for quantum gravity, obviously. And so an estimated temperature that high is probably good. It's in the right range, I
Mhm.
think. So it's interesting. It's a little bit. The thing that I like about it is it's a bit. All of this stuff just falls out of like an analysis of the 600 cell and holonomies with the SU2 groups. Well, in this case, it's kind of a basic topological action in some sense. I just find that interesting.
The
That
lattice quantum gravity type thing.
yeah, that you can arrive at something that gives kind of cool answers, and you know, um, and maybe investigate it more from different perspectives. But so that's going to be one that I'll write up, and that's it.
You
So
can put it into a quantum cosmology project, simulation project, quantum cosmology simulation project.
yeah,
You can.
because I think that would it seems right. It's getting to that. Obviously, I put a lot of this stuff to. This is not ChatGPT 5. It's Copilot, which is not as good as ChatGPT 5, but it's so some.
Or you are getting the code from that. Are you getting the Python code from that? Okay.
Well, yeah, it kind of
Or you make it.
sparked me to do the whole holonomy thing. So, which because like I was saying, I was working with these finite, although this is still a finite group, but it's just
Hmm.
interesting to explore these things from that. So, like I asked it questions on why this fit is not correct, and it tries to explain that. But so this is not really too important, I don't think. Oh, there is actually an interesting thing. So basically, we have a heat map of the not invariant values between SU2 and then the SL2C matrices. So SU2 are like the quantum kind of matrices, and SL2C then are the more space-time kind of element. And then when we arrange them, so we have the 120 of each, because we can convert the SU2 to the SL2C, and then we can cross multiply them to create this kind of heat map, which it is what it is. But I just kind of noticed that this section up here is a bit like the entire thing. It's almost self-similar. So then I was wondering, well, maybe there is some kind of
micro to macro connection.
Yeah, like a fractal kind of connection between the two, scale invariance. And so so it kind of prompted it then to look for the fractal dimensions and different things, because we have the statistics up here of a mean value, this, and a standard deviation of that kind of thing, based on this. And then when we do,
so you come up the Hausdorff dimension, the fractal dimension.
Right, there is a fractal dimension there as well. So when we look into the submatrix statistics, so it's talking about this. Basically, it just has very similar attributes, which is not unexpected, and it just confirms what we're talking about. And then for a fractal dimension, it uses you're right, 1.7905. So I kind of like looking for these values.
Like snowflakes, I don't know. Snowflakes have 1.3 or 1.4.
I'm not actually sure. Yeah, I forgot. It was a 1.6 or. Well, I did look up to see what else has a fractal dimension close to this. And interestingly, it was the city of Beijing in the year projected in the year 2027 or something like that. So I think it's very interesting, because that they would basically they're interested in excuse me, in China they want to do city planning basically, and they want to know how dense the area is, so they do like a fractal dimension estimate of the city to see how it'll grow. And so I don't think it has literally nothing to do with this, but so I'm interested in that though. Also, fractal dimension, I mean, it's cool and all, but it's not like if I used a different method other than box counting, which is probably if I used like a different distance measure, you'd get a different answer. So I don't think fractal dimension is like
invariant.
Yeah, it's not. Yeah, I don't even think it's just not something that's very nailed down. There's different methods, and you'll get different results. So that's probably why this turns up nothing. But who knows? And that's probably about it. Oh yeah, we can get into partition functions. I don't know. Obviously, I've done more work on this.
Are you loading directly from ChatGPT to this one?
Well, this is a no. This is a notebook. See that? This is an iPad, like a Jupyter notebook. So that's all.
But all these the text you get in the same the Jupyter notebook, you get the same text.
No,
this text, everything is.
No, I inputted this text. So, for example, I asked Copilot questions on why this didn't fit, because it's supposed to be a fit, but it obviously doesn't fit. So I was trying to figure out why it doesn't do that. So I basically it gave me an answer here, and I just copy and paste that into the notebook. And then I would use Markdown language to get all the equations, and then convert all of this document into a LaTeX document with all the equations and explanations and
So
graphics.
that's why I have the problem because I get the equations in the chat GPT,
Right.
but when I try to paste it into the Word,
Yeah.
you cannot direct. It doesn't show
Yeah.
the same type equation. It shows a different thing. How do you convert it back to the proper equation format?
Well, what you can do is
That,
ask it to output all equations in
uh,
LaTeX format, and then
uh,
you can take those LaTeX equations and either put them into the equation box up in the corner.
uh,
Because I don't use Word, so I couldn't for that purpose. So
oh,
I don't know if you can directly just paste LaTeX equations into the equation manager. You probably can. You can certainly, if you start using LaTeX or whatever it's called, or Overleaf, you can do that, or any of the other multiple copies of those. But the other thing you could do, Rajan, is right click on the web page that you're using. So let's say you're using ChatGPT or whatever on the internet.
uh,
Yeah, you right click somewhere on the web page of that space, that conversation. Probably not inside the conversation, but somewhere around the bounding box. And you click on the gray part or whatever, and then you select view source code, and then
oh,
it will give you the entire chat as just plain text. You'll have to
uh,
probably scroll way down, and then it'll say stuff like "you said," and then it'll say "Copilot said," and then I think you can copy all of that as plain text into your document, and then you'll still have to fix things, but it'll be a
HTML
lot easier.
is like a HTML code type thing.
Yeah, you see, well, it's something that I was attempting to do, um, because I was running into the same problems as you.
Uh,
Basically I had done all of this.
yeah,
Because you sit down with these large language models, and
like all this Z equal to sigma something. When
yeah,
it puts that, it kind of weirdly puts something in the word. Yeah,
exactly, yes. So what I did was, because you can generate so much output with these large language models so quickly. You can
yeah,
just have like conversation after conversation, and they start building
yeah.
up, and then you have to go back
Oh yeah.
in and sort out, well, what is correct here, what is usable, what's good, and what's bad.
It's
But
like editing. It takes
you have a
forever. Yeah,
record of kind of everything, and that's what this document is. It's a record of maybe 3 or 4 different
that's a
conversations.
good one. Yeah,
Yeah, but then I convert this into an actual paper later on. But I
uh,
couldn't do this. I couldn't. This was actually quite difficult to do. There was a lot of steps
yeah.
that I needed to do to convert this into a LaTeX file, for instance, because you can imagine how many errors are going to be thrown up
Oh yeah.
converting this into a LaTeX file. But I did it anyway.
I
But I
literally, what I did literally is that, see, in the word there's something called write your own equation. So you go there, click, and you start writing it out, and then it'll print, it'll produce. So you actually write it down, the actual, and then you convert it.
oh,
So
that's
I
good.
found
Okay.
it's tedious, but it still is more accurate.
Right. Okay. So the idea then is, because I didn't want to go through this process again anytime soon. I've the new method was to go back into all those old conversations that I never asked it to give a LaTeX output, and just right click, go to view page source, and then copy
Yeah.
all of the code directly. So you don't have to go in and like highlight each thing in each word box. You just highlight the page and
Yeah.
copy the text directly into a Word
Ah.
document, and then you have to go in and start fixing the code. But it will have the LaTeX in there. It will just
Mm.
be. It might say, instead of z equals this number, it will be
Mm.
zz equals this number,
Ah.
not properly formatted. And then directly after, you might have like a bracket, and then this will be perfectly formatted in LaTeX code, and then end bracket. and then you might have it unformatted again. So it like repeats everything 3 times for some reason, but the middle one will be
Yeah,
perfectly
I used
formatted.
to do that, but right now it's not doing that. I used to do like that, but it's not doing like I don't know what happened. But
Well,
because
yeah.
because
Anyway,
there is
so
a
that's
there
the
is
way to
also
do it. That's only if you have like historic conversations that you want to keep a record of. I would recommend that. But if for going forward, I would just ask it to output the all equations as LaTeX in LaTeX because why not?
uh,
It's just easier that
uh,
way, right? And
also
we want to move fast and make good discoveries. We don't really care how we do it. All right.
yeah.
So summing energy density. So these are just different things. I mean, obviously, this is going to be interesting from the point of view of the new research where we have a torus
Mhm.
ring and we have the helical winding system, and that's all around the vertices as the dihedral angle grows or shrinks and the curvature grows. But yeah, so that feeds directly into kind of string theoretic partition functions. But these partition functions, I think, are more to do with see that. So yeah, so that particular partition function I was talking about will be bosonic, whereas everything we've looked at so far with all the SU2 holonomies, that's all fermionic. So there's a bit of a mismatch there that needs to be addressed, but it won't be too big of a problem. But that's one of the next steps that has to
So
take.
Z is the energy density,
There
the
is some.
capital Z
It
or
could. Yes,
partition function.
I think. Yeah, we get the energy. Yeah, but you can do it multiple different ways. I mean, we have energy densities coming from here as well. Um,
Mhm.
but that's the topological thing. And then the partition functions, this I think must relate more to the, oh well, it's been a while since I looked at this, to be honest with you. And this might be wrong at this. Oh yeah, so it's a partition function as a function of curvature, or then there's the energy density integration. So this would be over the cells of the lattice of the 600 cell using the SUT U2 matrices. Um, and so these are supposedly different ways of doing that. And you can just get so you're just summing the energies in each of the lattice cells based on the vertices. So that is that sounds maybe more like a loop quantum gravity approach as opposed to the string theory approach that we might deploy later on. We're kind of moving away quite a bit from any loop quantum gravity stuff in this research, which is good. Um, Even though I like,
But it's more lattice
well,
quantum.
yeah, but I mean, you have like lattices in loop quantum gravity as well, because the
Yeah,
loop is over um, like literal loops within the lattice, like great circles or whatever. I really like it. I think it's a great idea, but it's also something that's it's kind of someone else's idea, So I'm not going to sit just
yeah. It's a
working on.
structure,
Yeah,
structure based geometry.
it's Lee Smolin's work, and
Ah,
I like Lee Smolin. I think he's a cool guy. So anyway, here we go. Let's move on. Yeah, I think I kind of talked about. So there it is in no, more scientific
ah.
notation. 4.26 to the 10 Kelvin.
More
Uh,
than a billion,
right.
42 billion.
Okay. You're good at the big numbers there.
Yeah.
So, well, that's curvature versus temperature. So these are all, just ideas that we were knocking around with. Um, and then, yeah, so this is the curvature versus temperature kind of thing. I don't know how interesting that is. And that is really it. So I'll leave it there for now. How do I stop sharing?
You just click the plus button.
The X button. Yeah.
The square. Yeah, there you go.
Oh, it's very
Okay.
dark here now, so this is it's coming into winter, I guess. But yeah.
Ah, yeah, we are
Okay,
also. I mean, our
yeah.
temperature is higher than normal. I mean, it's coming down, then going up, but the fall is already here. But the temperature is going to be higher. It's almost like summer, like still. The
Oh,
fall
right,
is.
great. Oh, well, so what's your winter is going to be crazy? I hear. Possibly they're projecting the winter in the U.S. It's gonna. There's a possibility of a country being sort of divided uh, through the center, and then you're looking at in your area in the south, in the desert sort of regions where in Nevada and stuff, you'll have a lot less rainfall, like warmer temperatures. You're going to have quite a nice summer.
It is less than normal, but they think it won't be. It will have. There are some showers happening, but it's not sufficient enough
Yeah, that's right.
to overcome.
And
Yeah,
yeah, but then the north is going to be. So I hear anyway. These are just based on climatology
a lot of
models,
flooding and everything is happening everywhere.
right?
Flooding and
Okay, I didn't know about that, but apparently snowstorms and will be intense. That's what the
Hmm.
models project. And the big issue though will be the line where the cold front meets the hot front. There could be a lot of storms and flooding there in that region. So hopefully that doesn't happen. Uh, Hopefully you have a nice winter. But those are
Yeah,
the projections. So yeah, so it is interesting though. So I don't know what's causing that. That could be something to do with the polar vortex, and also it's related something to do with El Nino or La Nina and all
yeah,
of that. Apparently, which is such a weird thing because it's like some sort of jet stream that's coming out of South America somewhere, and that used to be a big thing. I remember people talking about that, and it's like, oh no, this jet stream thing is going to screw everything up and create all these problems. But now it's like it isn't there, and there's something else or something gone wrong with it or something, and there seems to be this even larger catastrophe to do with
so
the.
microbursts. The biggest problem is microbursts, where very highly concentrated areas get this storm, but other areas will not have that, and they create havoc. I mean, they create the all these tornado type things,
Right.
different places, and they destroy property. I mean, they have so much pressure, they destroy everything inside that. It's like a like a black hole effect. It has.
Sorry, what's it called? What's it called again?
Micro microburst.
Oh,
It's like a
I've not
micro.
heard of that.
It's a
I've heard
very
of
localized storm.
there's something called
Microburst.
a Duraco or a Duratio or something. Duraco. It's like a hurricane, but it's a kind of straight line hurricane. Anyway, lots
Yeah,
of yeah.
yeah, it is very vortexing thing. Also, a lot of these are forming in the
Huh.
Pacific or Atlantic Ocean. All these
Yeah.
storms are forming, and
Well, actually,
some of
I've
them
heard
go
the
away.
number the number of
Category, they
tornadoes.
increase the category storm. The category increase sometime when it comes towards the shore. Sometimes it decreases. So it is kind of
Okay.
yeah.
Well, that's interesting. Apparently the number of tornadoes in the Atlantic Ocean during this time of year should be quite high, but there haven't been that many. Much less than they were expecting. But there have been a couple of big tornadoes going off in the Pacific Ocean. But that's fine for you guys because that travels away from your country, up towards wherever.
No, the Pacific coast is near California.
I
So what
know.
happens is lot of times
Oh, yeah,
when it comes there, it kind of veers away, but it will produce a lot of showers. The
right.
storm will come but it won't create that. Sometimes there's wind, but it won't create the tornadic effect in the sense
Okay.
that it won't create all the tsunami type thing.
Yeah.
But It'll
the
create
it seems to be going
showers.
more kind of away, like it'll hit you maybe, but like at an oblique angle. It's not like
Yeah,
traveling right. It's not going towards landfall. I don't think so. Obviously, they could curve up and do that, but
yeah.
maybe that would be like an unusual event. Um, but yeah, so that's interesting. The Yeah, today, like as I was saying earlier, there was a lot of wind around here, and there was a lot of vortices going around. All, but it was
Oh
all
yeah.
very gentle, and they were all like flowing into each other. It was very cool. So that's why I had to get out today for a bit of a walk. As you can
What
imagine,
we
in,
what we get
in
a
Chile.
lot is something called a haboob. Haboob is like a dust storm, a huge dust storm.
Oh, okay,
Uh, it's like in Sahara, I think they have very
yeah,
similar thing. So they throw away dust. All the cars, everything be filled with dust,
right.
and
How?
there won't be any rain or anything because lack
Yeah.
of moisture. Lack of moisture. Just dust. It carries the dust and just dumps the dust all over the place.
So how often do you
So
get those?
there were already twice, two big ones, very close to my home also, not too far. Uh, and they create the main thing is lot of dust everywhere,
And what's
and they
what's
can
the
create
reason?
problem. They can create traffic, especially if you are driving. The visibility becomes zero, almost
Oh,
close to
zero.
zero.
Absolutely, yeah.
Yeah.
That's
So
interesting.
yeah, it does. And
And
now the airports are shut down due to different reasons. Not only the climate, but they said Europe they had a problem outage because it was a hacked internet or something. I don't know.
I did not
Yesterday or
hear about
today.
this. Is
Yeah,
that
yesterday or today. Many
oh, really?
airports. Yeah.
Oh,
So
interesting.
people are stranded. People are stranded.
Oh my God, that's terrible.
Uh, yeah. Here
Well,
also
that's
it's
if you're
happening.
just doing
So
it in an airport, well, it depends on the airport, but um, I wonder, do they look after you? Because like airports are expensive,
oh yeah.
Yeah. Um,
But
but well, that's it. So I mean, there's been a lot of happenings in the media recently as well, but um, not so much from a scientific perspective. There seems to be kind of a low number. Well, I suppose the big thing really is all of these AI artificial models, which is
yeah.
like a major advance, I think. And I think in the next 5 to 10 years, we're going to see some really big advancements from a scientific perspective. So that's going to be really interesting. I'm looking forward to it. But
So I saw a couple of pictures I got. It's again final thing. So this you see. Oh, so I have this problem in the thing that I have to get rid of. I don't know how to get this kind of internet like a cookie or something that's coming up. Okay. I don't know this only way. Okay. It takes away time.
oh yeah,
Mm.
I don't know. Does that you've had that thing for ages where it pops up where it's like some
Yeah, it's a pop-up, like a pop-up, you
viral
know.
total thing or something? It's like
Yeah, some viral thing because
what
sometimes
magic?
you have to allow some cookies and then these things start popping in. And then it's very hard to remove this stuff. Anyway,
I don't
so
know.
I found a way to remove. That's the only way I know able to remove that. Okay. So now
Yeah.
let's see. See, one of the results is this one. See, the interesting thing about is that I come absolute theory, right? Then I convert to monopole and superluminal thing.
Yeah.
And so I'm coming from two different directions. And
Huh.
it's showing there's some convergence. Uh, it's showing, give me a convergence result that you can create a micro black hole from this. It's a dipole monopole interface.
Right.
So the monopoles exist in the superluminal condensate. and the dipoles exist in the observable universe, in the in the real world. So when you combine that interface, you get a micro black hole. The what you
Yeah.
call decoherence, coupling strength. So I can convert into equations and things like that.
What
So
is the white
very
point in the
interesting
center
thing.
what's the white point?
Uh,
Sorry,
and
Rajan.
the other, yeah,
What's the white point in the center of the graph?
the white, yeah, that's where the vacuum.
Oh, it's a
It's
critical
like
point.
a vacuum
So
inside a
is
micro black hole.
that's not part of the scale, color scale on the right though. So you've added that in.
No, it actually puts it in. I have just programmed it. It puts it.
I
So
know, but
phases.
is that is like a separate trace in the diagram. Okay, that's fine. I was just wondering. So,
Yeah, I had to find out. I'm going to look
so
into that little more.
yeah, so
But
you've got a curvature scalar there, and what's the other? What is the other decoherence coupling strength? So what does
yeah,
that mean, Rajan? Decoherence
the
coupling strength.
the coupling is between the gravity. This is like a strong gravity, weak gravity thing. So the coupling between the dipole, the magnetic monopole, and the dipole, how
Oh,
they couple together.
okay. So how do you
Uh,
calculate that?
so they either produce coherence, like entanglement, or the opposite of that is a decoherence, right?
Oh, okay.
Opposite of the,
Yeah, yeah, of course.
yeah. So it can,
So
like, very
why is there a
similar,
coupling strength related to decoherence?
yeah. Decoherence, you can think of this way. You have you found a closed loop, right? Closed loop magnet. It's like coherence, or entangled. And uh, and an open string is like decoherence. So you can create coherence or entanglement, and you can also do decoherence where it distributes in the environment. It becomes part of the environment, right?
Uh,
So the environment, it concentrates and forms like a small mass, and which entanglement or coherence, and then the coherence goes away entropic and becomes entropic, and it dissipates into the environment, you know so
okay,
yeah, so that's the idea of formation of matter or particle, and the particle then becomes like a wave. So wave and particle kind of thing,
okay. And so
or a
why is
field.
there? All right, okay. So it sense why is there a coupling strength? So the coupling strength is
So
between.
there's a coupling strength that decides uh, which way it's going to go. So, whether it's going to go coherence or entanglement, or it's going to decohere or distribute in the environment. So,
Uh,
see, there's a coupling strength between gravity, electromagnetism. There's also strong nuclear, weak nuclear.
yeah, I know that.
Uh, th-
I'm
yeah.
aware of those,
So,
but yeah,
so
this is a bit unusual. I don't know about this, but I suppose it's an idea that you're kind of coming up with. It looks like I don't see how you can put coherence coupling strength on the bottom there and curvature on the right. Are you saying it's basically a one-to-one equivalence between these two things, that one is the other?
yeah, it seems like, because the curvature, see, initially you have the superluminal condensate, which is random fluctuation. It doesn't have any curvature, any specific curvature, right? Like your infinity thing, it's like flat, or maybe slight fluctuation, very,
Yeah,
very minute fluctuation.
yeah. Okay.
But when you get localized, there is some localized events that's happening, that is curving the thing and forming like a particle, like a field is curving the field and forming like a actual particle. That formation depends on the coupling between the what is that field, the local field, and the global field. you know so
Well,
how
that's
that coupling
interesting.
strength.
Yeah, because with the model that I'm working with, let's say in the simplified version, you have this two-dimensional hyperbolic
Uh-huh.
pentagonal tiling, and as you
Uh-huh.
increase the tiling number, and you have the torus then that I was talking about, this
Yeah.
this ring kind of thing around each vertices, each vertex, sorry. And then as the as you increase the tiling number, then you increase the curvature essentially. So we're saying we're putting it equivalent to curvature in an abstract sense.
Mm.
And then so the torus grows as well. But then I was thinking, well, if you can link the area of the torus that it creates and say like, okay, so you have a kind of a time evolution of the Schrodinger equation where
Mm.
the particle begins to spread out more as the curvature increases, as the time continues. But then I was like, that doesn't really make a lot of sense. So it's good fun. It's a bit like what you're doing here, relating curvature to coherence in a sense, right? But if so,
Yeah.
so it's like saying if someone were to measure the particle, it would snap back to like close to the link complement because it would become like way more coherent. But the curvature would still be large, but that wouldn't really matter. So it kind of decouples the torus from the lattice. Then in that sense,
Hmm.
the, the the torus could grow and shrink or spin and slow down. Well, it was mainly the speed of that the torus is rotating around the link is is definitely variable, because then that will depend, that will, when it's projected then into Euclidean three-dimensional space, it will tell you where the particle is roughly because of the uncertainty, and then also its speed and all of that jazz and nonsense. So, but the main thing then, I think, you're saying, so the model that I'm generating, if we were to say that the area was linked to the uncertainty, or the decoherence, if you like, the Schrodinger equation, time evolution, then as the gravity, like the curvature increases as the gravity gets stronger, the more uncertain the particle is. And I just don't think that's the case. So, what do you think?
Oh, yeah, it's interesting thing. Einstein says that gravity is nothing but, the curvature of space-time creates the gravity, right? So that's a relativistic point. That's where the whole problem is. The relativity, general relativity says that it's the curvature that's creating the gravity, not Newtonian way. Uh,
Right.
but the
Well,
quantum,
think about it this way, Rajan. So if the particle is getting closer and closer to the event horizon, yeah,
yeah.
or the singularity, um, the uncertainty is going to be so high that the particle can be both inside or
Hmm.
like trapped
Yeah.
forever, or it can like escape as Hawking radiation, right? So
Yeah.
that's so basically there's a theory, there's the theory that if you were to fall into a black hole, that the laws of physics break down, obviously, but more importantly, we're talking about like that the uncertainty of your position within the black hole but would become so uncertain then that you could appear outside of it, which is kind of the same as the laws of physics breaking down, which I think is pretty cool. So, I mean, in that sense, that seems to suggest that at maximum curvature, you also have maximum uncertainty. So maybe there is an argument to be made for, particles closer to a gravitational well, their wave function becoming more uncertain. And I suppose that makes sense in some sense because they're perturbed more by the holonomies, and therefore, you know, their chaotic movements, like their perturbations, are going to be more intense. So their deviations. So maybe there is something to that. I just personally found it a bit odd to consider, but I think it's something you seem to be suggesting here as well to some degree. So,
Yeah. Yeah. So, see, I did it from materials, from thermodynamics point of view, and I even conducted experiments. So, what I believe is that, it's essentially entropy, a disorder, right? So, highly disordered, chaotic thing, right? When it goes above certain level, it started to become ordered automatically because the
Oh,
energy is so high. And I kind of proved it with the formation of a diamond. So I did for the Navy. I think it was a Navy project. I did like more than 30 years ago. So it's a defense project. So creating a diamond room temperature. So the graphite, I disordered the whole graphite, right? Under scanning tunneling microscope, I disordered it completely. And at some point, the disorder is so high that it clumped back together and formed like a small diamond nuclei. So at a very high level of disorder, the energy becomes so high that it collapses, automatically collapses to, uh, you know, uh, a particle. So if the field, for example, you have a highly chaotic field, right? Very disordered field, if it's very high, when it goes very high, the energy is so high, it collapses and forms a particle automatically.
oh, that's
So
interesting.
I think,
Yeah, 'cause
yeah,
that makes. I mean, that's kind of a little bit related to what we were talking about earlier, to do with, as a particle travels towards the speed of light, you know, things
yeah,
happen, right? But then if you were to go twice the speed of light, and then 3 times, and then 4 times, then
yeah,
what you'd find, like, that it's rotating through the fourth dimension, and it comes back to the point
yeah,
that it was at
yeah,
originally, which indicates that it's no longer traveling at that point. It's now stationary again, which is a funny concept. And so that
yeah.
kind of
So it means that
it's very
initially
interesting
it is
that
like a,
you say that, actually, Rajan, because I was thinking, like, there's another guy who's actually a physicist lecturer. He's kind of famous for being homeless or something like that. In the
oh,
Yeah, he's working for UCLA or something, or maybe he
ah,
graduated UCLA. Anyway, so he's just very annoyed that he's not getting paid enough to like
yeah,
rent his apartment or something like
same
that.
thing. Yeah,
Yeah, and then he's like professor or adjunct, maybe, I'm not sure. Anyway, but he was talking about a concept that if you were like in a spacecraft, let's say, and you could travel at the speed of light, then you're going to undergo length contraction, and and then at the speed of light, you should be like entirely flat. Now, I think, actually, based on other results, that it might actually be not just length contraction, but a complete contraction of all dimensions, like X, Y, Z. They'd all shrink at the same amount. That's what I think happens, but could be debated. But the point is that would imply that all the fermions in the craft are now all going to be sitting on top of each other, but that's only from one perspective. But let's say that is true. Then that
mm,
obviously a fermion with the same state cannot occupy the same place. So his
yeah.
point is that all of that matter must convert into bosonic matter, which makes sense. I think Gerd did work
Oh,
on this.
the photons can do that, right? Photons
Yeah,
can go into each other.
exactly. So basically, if you're traveling at the speed of light under the general relativity regime, you will become light. Like, which
Mm.
means you'll just like
Interesting.
explode into a ball of
That's
flames.
very interesting. Yeah.
Yeah, which is what I think Gerd proved that, with some equations. But it's kind of I figured that out when I was about 10 or something. So but I
Oh.
just but Gerd actually has the equation, so that's more impressive. Anyway,
Quite
so
plausible. Quite plausible explain thing of what really happens. So we all become light, uh,
right, but
and
then
that's true. Our soul may be that way. If you look at back the theology,
yeah,
how the body, mind, and the soul exist, right? The soul is like a light, right?
yeah,
And the mind and the body. The mind is the interface between the body and soul, you can say.
yeah. Well, do you remember
So,
I wrote that book called what was it? Siempre Brocade, the cataphysics book, and I talk about that, about how there's this, or well, it's something to do with, it was some weird concept anyway about things. Anyway, we'll get into it later. But it was to do with the speed of light and length contractions, and then expanding again. But actually, if you think about the length contraction, point for a bit. It's kind of interesting because if everything is going to be squashed down, like let's say I'm correct, and all the different dimensions are getting smaller and smaller, then at a certain point you're gonna become quantum in size, yeah, because if it collapses
Yeah.
zero, you're gonna pass this barrier where like the length is goes into the quantum world, and then at that point everything will become uncertain. It's like we no longer know the position of the particle, and if we did, its velocity would become infinite. And if we knew its velocity, then its position, that, so to be like
Yeah, we don't know we are in the particle or the in the wave. So,
yeah, exactly. So you'd have a particle wave thing, Heisenberg uncertainty. So now you're talking about linking Heisenberg uncertainty with the with special relativity, which of course has the time dilation and length contraction effects, which are also linked to the gravity of general relativity. So now we have a full path from Heisenberg uncertainty to general relativity, which is nice, and sort of links to what you're talking about. Yeah, so basically it implies that as we move faster towards the speed of light, the uncertainty will get greater, which means also the disorder of your of the particles in your body. Becomes more disordered, more decoherent, right? As time goes on, and it also equivalent to crossing the event horizon, where like your position becomes uncertain to the point where you can even be outside the black hole again, and then so you get what I'm pointing. So that then connects relativity to the special relativity case. So that's good. But there's another point here that I'm missing. Oh yes, going back to your point about the diamond, so the more you increase the chaos, if you like, the disorder, the more ordered it becomes. But then if you kept doing that, like if you up the energy even more, you could break it all apart again,
Again, disorder. So it's like a fluctuation. It goes to disorder, order, then disorder, order, like that.
Yeah,
It can keep fluctuating.
But each one would probably need like an exponential amount of energy to get it back to that level or something. And so at that point, it might even be like, it might be outside of the scope of reality for those types of energy to really
outlier. Yeah, the graviton may be something like that. Graviton may be something like that.
Right. But I suppose even the particles themselves would lose. So there might be like different types of order that you're looking at. But yeah, so that would be interesting.
It could be.
You can think of it. Decoherent at the speed of light, matter. Like, assuming it was possible. And then if you were to keep traveling, you would like recohere and like
coherent.
Yeah, but then what would you be? It's interesting. Anyway,
like graviton may be like that. The graviton.
Go. So it was nice talking to you, and I'll see you in a week's time or so. If you want to continue on.
2 weeks. So this is the other one. Now I'm talking briefly. We'll talk next time, but finally I put them together in terms of time and memory, all these things.
All right.
So it shows here. I'm looking into that. This is the theory I'm looking further. The predictability. It says the decision boundary of predictability. Coming up with that. So where events can occur, where events may not occur. So the future, I'm trying to put it how it progresses over the decades, and maybe there is a time cycle that goes in. So probably next year it could come back and become uncertain, and certain things can occur depending on what lights up. So it shows that next year it could be some cataclysmic events. So I'm checking whether that is happening, because the good thing is the ChatGPT can pull up that.
I need to know a lot more about what all of this is. You've got memory, and you've got what?
Time, echo time. Echo time is like a time that that connects with the past and the future. So
Okay,
it's
yeah, that's
echoes
fine. But
between.
if you're going to show this, you have to show the data. You have to show like what the points are. I'm guessing this is just what's the word? This is just a simulation. There's no actual data here. Is that right?
Yeah, it's a
Okay.
simulation, but it uses some data. So I kind of put it together like
Okay.
this,
Yeah.
and
I mean,
I
obviously, like it's a simulation, but you'd have to show what the data is. You can't just say it uses some data. Like I know, like
yeah
what's an event? Like you've got time. So you're saying there's certain events and then they happen in memory. So and
yeah.
then what's the decision boundary? Is there any points here? Yeah. So are there any points on the other side? I think also you need to work on your color coding because it's a little bit difficult to see the brown specks on the dark blue line.
Oh, this is the event where the events can
I can
happen.
see those.
Where
I
this
can see
is.
those, and I can see them, but
Oh,
I don't know if
yeah.
there's any on the other
Oh,
side.
this one you mean? Oh, this one. This is a
I can see
boundary.
them.
Yeah.
I'm not sure if I can see. So also you've got a boundary there. So like, what's on the other side of the boundary? Is it just emptiness or?
Yeah, it's like a firewall. It's happening.
Okay, so
So
you can't remember past that point or something.
yes, yeah,
Terrible
we cannot
long-term
remember. Yes,
memory problems.
yeah.
I
So
understand.
I kind of put together into a graph, and I'm working on it right now. So
Okay,
if I convert this, it means that
is
there
this a
are some
time?
events,
Is
and
this
I
a time
find some
loop or something?
correlation that things happened in the 2008 level,
Yeah.
and then as we go on, this rotates, and then the time. So next year it could come back here, 2026. It could come back again to this type of clustering events, and I'm
Uh,
checking whether it is a possibility. So then, if it is so, then it can create cataclysmic events next year that we don't know yet. So
okay,
that's what
well,
I'm trying
you
to
have to
figure
show
out. Or no event.
why that loop is a thing and why and what was the cataclysmic event in 2008 that's going to repeat. Oh,
Yeah,
that
I
must be
read it,
lucky.
trying to remember. Yesterday I was reading, and
Yeah,
it somehow made sense to me. It
yeah.
was something that happened with Earth or something that happened during that time. And I had to pull back. I had to go back and check.
No,
Suddenly I
I'm
forgot
sure there
that.
was a disaster. I just can't remember what it was.
Or it's astronomy, some astronomical event. Very
Okay.
similar to the alien, what is that entity that came in that 20 that was connected to 2012 uh Obanovia or something like that. What is it called?
Huh?
That thing that passes by the Earth.
Oh,
It
Uma
almost.
Mound, the big rock.
Yeah, Ob something.
It was just,
Obi.
we should just call it Rama. What about that?
Yeah,
Yeah, because it's easier
Rama.
to remember. No one can
Yeah.
pronounce the other one. Like Rama was a book by Arthur C. Clarke where it was this big alien spacecraft that flew through the solar system, and they called it
Uh,
Rendezvous with Rama because they were running
uh,
out of Greek names to call objects in space, so they started to switch to Indian names instead. And I always thought that that's what they do, but instead they decided to pick a Hawaiian name, which is fine, but it's just very difficult to pronounce. I think it's Umau Mau Mau Mau.
oh, something like that.
Nobody can do it.
Yeah. So
Like if you're not pronouncing it every week or like at least
yeah,
once
it's very
every
hard.
couple of
Tongue
months, you're getting
twisting.
better.
It's a tongue twister. Yeah.
It is a bit. It's kind of cool though. So I don't. Yeah, there's a new one of those, the 3IA Atlas thing, um, and they're saying that it's there's certain scientists saying it's an alien spaceship and it's going to attack Earth in November
Yeah,
25th.
actually, there are things going on in the Congress, the
Yeah.
UFO thing,
Oh, great.
and they're starting to accept the thing that pilots, the Air Force pilots, and other people,
Oh, of
they are
course.
proving.
Oh no,
Actually,
there's
you
definitely
cannot put
something out
anything
there. I
else.
just don't know if these asteroids are the thing, but they are interesting though, aren't they? Because when that interstellar object passed through the solar system, they were like,
Uh-huh.
"Ooh, this is like a really amazing event, like one in a gazillion chance or whatever it is, like
Yeah.
it's going to happen again for another 500 years or something. I don't know what it was, and then it just happens again the next day, like basically the next day. You know what I mean? Even though it's a couple of years later, but it really the probability of an object like that coming a different, but an object all the same doing that from coming in from interstellar space is highly improbable. So I mean, there's some people suggesting that we might be moving into a field of objects like this, which would be terrifying. But uh,
Intelligence.
the,
So
the
the
other
question
the other
is,
the other theory is that it's an intelligence sending them here. Yeah, so it's really interesting. Um, so it's not completely unfounded. It sounds like sci-fi nonsense, but maybe there's
there could
certainly. I
be
think if the
something to it.
theory was to pop up, then I would really start being like, okay, this is weird. But at the moment, I just think maybe it's a freak thing. Um, I don't know. I think it's probably a rock. Yeah, I don't think it's an alien spaceship. That's my opinion. But there
We'll
are
see.
people talking about what that it's plated in some sort of metal or something, and it's got some weird aspects to it. It's, you know,
Maybe from your lattice quantum gravity, you can say whether it's intelligent or not. Yeah, we can come up with something that
mm,
will gauge, like a gauge intelligence, and say whether that has intelligence, what we
oh,
call it intelligence or
well, I
not,
think that's
or it's
very
just
much
a
outside the
freaky thing.
scope of my research. What I've got basically is just the interesting thing is you're dealing with general relativity, quantum mechanics, and then basically you're sort of widening the net constantly, so that your
With the
theory then
geometry, group
starts to
theory, and
starts to encapsulate things like thermodynamics and entropy, and so on. And you just keep like subsuming more and more concepts from physics, and then once you get all of the links um, together, then you say, oh, okay, this is a theory of everything. But it's not like actually a theory of everything. Like I can't use it to decide whether the person down the road is going to buy milk or bread tomorrow.
mm,
And I don't care either way. Okay, but I'm gonna go.
okay.
See you later.
Thanks a lot. In 2 weeks, we can make it every other week. So
Yeah.
in 2 weeks we can come back.
Okay.
Uh,
Cool.
because yeah, I talked with
Yeah, because
Emery one
we're
week.
we're all
No,
busy. Yeah. We're it's a busy time of year. So
so it's helpful. Every bi-weekly, every 2 weeks will be good.
good idea. Good idea. Great.
Yeah.
Okay.
So we
Great to
will
see you
meet
guys.
on the 4th, I think, 4th of October. It looks like.
Okay. Do you want me to end the stream then? Yeah.
Yeah, we can do the streaming on the 4th.
Okay. But I'll end this stream.
We can end this stream now. Yes, thank you.
Okay. Cool. See you later.
Okay, have a nice week. And then